everyone, and welcome to Hour of Code with First. My name is Libby Kamen. I'll be your host today here on First TV as we celebrate Computer Science Education Week with a series of fun and engaging activities. As a proud First alum, I'm incredibly excited to be here with you all during CS Ed Week. Whether you're joining us to build and test code on your competition robot, using the robot simulator software, or participating in our cardboard robot project, this Hour of Code with First will be a great time to deepen our understanding of code, robotics, and computer science. Today, I'm joined by Brad Miller and Grant Perkins from the WPI Control System team. Before we get into all of our awesome activities today, I have a couple of other fun things to share. Earlier this week, in celebration of the release of LEGO Star Wars Holiday Special, streaming on Disney+, Star Wars Force for Change, Disney, Lucasfilm, and LEGO teamed up with First to bring an exciting STEM challenge for all of our at-home innovators. Here's a special message from Kelly Marie Tran with more details.
Hi there, Star Wars fans! Kelly Marie Tran here. In the LEGO Star Wars Holiday Special streaming on Disney+, Rose, Rey, Poe, Finn, Chewie, and all your favorite characters come together to learn the true meaning of Life Day.
Gimme! Galaxy's best emperor! Meh!
Now, with the holiday season upon us, we want to keep the Life Day magic alive by seeing you become forces for cheer. As part of the Star Wars Force for Change initiative, Disney and Lucasfilm are once again teaming up with the global robotics community First to bring you an exciting challenge. Through First LEGO League, students around the world are introduced to the basics of robotics and engineering, using LEGO bricks to build unique solutions that teach coding, creativity, and teamwork. Together, Star Wars Force for Change and First are challenging you and your family to put your design skills to the test. We want to see you reimagine your LEGO bricks into Star Wars holiday-inspired builds. That icy rebel outpost? A winter wonderland. Those colorful lightsabers? Twinkly festive lights. The Millennium Falcon? Try the fastest present delivery vehicle in the galaxy. Share a photo of your reimagined LEGO Star Wars holiday-inspired builds on Instagram or Twitter using hashtag LEGO Star Wars Holiday Contest. And don't worry, Rebels, this is not a trap.
It's a wrap!
5 winners will be chosen to receive some exciting LEGO prizes. Our grand prize winner will receive a LEGO Star Wars Millennium Falcon and a First LEGO League team or classroom registration.
So cool!
And 4 runners-up will receive a LEGO Star Wars Sith TIE Fighter, Poe Dameron's X-Wing Fighter, an AT-AT, the Razor Crest, and the Child. That's 5 things. Not a bad bounty, right? So come on, builders. You're our only ho-ho-ho. See what I did there? And be sure to check out the LEGO Star Wars Holiday Special, streaming now on Disney+. And may the Force be with you.
That looks so cool. I'm so excited to see all of your builds. I may just have to make one myself and try to win some of those awesome prizes. There are so many different things that we're all doing at home now, and this could be one of them for the holiday season. So make sure you check that contest out. Of course, we're all doing a lot of things at home, and throughout this year, many nonprofits, including First, have been affected by the COVID-19 pandemic. As 2020 comes to an end, First is seeking your help to alleviate some of those challenges. For those of you who are a part of the First community, please consider giving back so that future STEM innovators like yourselves can continue participating in new challenges and projects from around the globe. For more information on how to support, please visit firstinspires.org/give2020. With all of that said, it's time to get into our amazing Computer Science Education Week activities and our Hour of Code with First. So like I said, I've got Brad Miller and Grant Perkins from the WPI Control System team. So guys, what are we getting up to today?
Hey, good morning, good afternoon, and thanks, Libby. Hey, we're going to talk about how to use the WPI Lab suite of software to write programs for your robot. And we actually have a lot of pretty interesting things to talk about. So we're going to talk about how you can write programs using the whole WPI Lab suite of tools, and that's going to be kind of exciting. But then we've got some a really interesting new robot that we want to talk about that you can actually use at home to learn about programming. And so we'll talk a little bit more about that coming up. And then we're going to talk about using and installing Visual Studio Code, which is the development tool, the main development tool that we use for writing C++ and Java programs for FRC. We'll write some simple WPI Live programs. we'll talk about how you can run those programs in simulation as well as on real hardware, both on this new small robot platform and on a real FRC robot that we've got here. And then we're going to talk about making more complex programs, which will be kind of interesting to get better control of your robot. A little bit about vision processing on a coprocessor, and we'll have an FRC robot that can drive around and look for a target, a vision target. And then we're going to talk about how you can get better control of your robot. So if you want to go beyond the normal things that you do to steer the robot and drive it around, then we're going to talk about how you can do that and some advanced things that you can look at. And to do all of these things, so there's myself. I'm Brad Miller, and I'm at WPI. I've been working on WPI Live since the beginning, since 2008 or something, when we did our first release of the software for the C-Rio, and then we switched to the Robo-Rio. And I teach robotics at WPI, but I spent a lot of my time working on WPI Live stuff, trying to get good software for you guys to use. And then with me is Grant Perkins. Why don't you introduce yourself?
Hi, I'm Grant Perkins. I am a WPI Live developer. This is my third year working for WPI Live. I'm also a FRC Team 190 mentor, and I'm also a WPI undergraduate, class of 2024, majoring in CS. So that's me.
Okay, so here we go. So there's the two of us, and then as a special bonus, we have a number of members of the WPI Live development team who are actually all over the country, kind of scattered around, and we're going to be adding them into the broadcast so that they can give you a little bit of extra insight into some of the code and some of the programs that they wrote that you guys probably use very often. And so that will be pretty exciting. And then the other thing is that this new robot that we're introducing is called the Romi, and it's kind of midway through its introduction. So you'll be learning a little bit more about it in the coming days. But there's a little bit of information on it on the WPILive.org website on the blog. And it should be the most recent blog post, and it kind of talks a little bit about the Romi, and you'll see more and more stuff about it coming up. So, what I want to tell people is, like, it's really important, is that when you're writing programs for your FRC robots, what often happens, and what I see, is that teams don't really get going full speed writing software until the robot is ready. And as we know, the robot is usually ready the night before our first competition, the hardware. And so that means that the software team only has like 5 minutes to make the software work. And that's really not a good thing to do. And what we want to talk about today is a bunch of tools that we have that will let you get going early. So you can start early, you can get going with programming, you can do stuff with simulation, you can learn about this stuff using something like the Romi or simulation, or the simulators. And in addition, we'll talk about some really cool ways of writing programs that are easy, modular, easy to test. So that's sort of where we're going with this. So we're going to talk about the software libraries for all these robot controllers. That's the software that controls the motors and the sensors and a bunch of other utility stuff that you want your robot to do. And the languages we're talking about are C++ and Java, although LabVIEW is another WPI Live language, and the LabVIEW team is actually working on adding support to LabVIEW so you can use it with the Romi. So as we're talking more about the Romi, if you're a LabVIEW user, then this should be available sometime soon, and so you can use it with LabVIEW as well. And then we're going to talk a little bit about this plugin for Visual Studio Code that lets you easily write FRC programs in C++ and Java, and a bunch of other tools. I mean, this is sort of what we do. This is the whole suite of tools. There's a lot of other tools that help you develop your robot programs, like Grip and Smart Dashboard and Shuffleboard and Robot Builder and robot characterization tools, and a whole bunch of other stuff. So we're gonna touch on a lot of that stuff during this time also. So so it should be pretty good. We're gonna try and go through and kind of hit a little bit about almost everything that's in the suite of tools, the WPI Live suite. Another thing I'll mention about this stuff is that it's all this stuff is open source. So if you guys are interested in knowing more about how it works, you can go on GitHub and you can see all of the software libraries, all the tools, all of everything. And we are always encouraging teams who find issues or want new, are looking for new features, or just want to in general give us feedback about the software, to go onto GitHub and submit issues. So that we can see those and respond to them, especially if they're bugs. And actually, it turns out there's a lot of teams now that actually find problems. They look at the source code, they fix the problems, and then they send us patches in the form of pull requests to try and fix stuff. And so we really appreciate that, especially around the both for the documentation and for the code. So let's see what's.
Brad,
all
I've
the
got a question
software
from the chat
is
if
all
you're
open
available.
source. It's all community developed. So everything that you're going to see today is all available. You can download it. You can look at it. You can see how it all works if you want. But understand that nobody's getting paid to do any of this stuff. This is all being done by volunteers in the FIRST community, and it's pretty exciting. I think we're probably up to like 500,000 lines of code that represents all of the software that we're supporting, and we keep adding more stuff all the time. So pretty exciting. So if you want to do this, if you're going to do this yourself, the first thing you have to do is get the development tools. So you have to install Visual Studio Code, and when you get the WPI Lab Development Tool Kit, the package, that includes the install or will install VS Code for you if it's not already on your system. It gives you the option of using the one that's there versus installing it again. And then the other thing that we're going to talk about is getting this image. It used to be called FRC Vision, but now we've expanded the scope of it. So it used to just do vision stuff, and you put it on a Raspberry Pi, and it would act as a coprocessor, and then you'd be able to have your robot talk to the Raspberry Pi and get images and navigate to targets and stuff on the field. We've expanded the scope of it, and now it actually does stuff with the Romi as well. And so we've changed the name to WPI Live Pi. So this is, and we'll talk about this a little bit more coming up a little bit later. The other thing you need for the development tools is to get the NI tools package, even if you're not using LabVIEW, because it's got the driver station and the thing to image your Robo-Rio, if you're using a Robo-Rio. If you're just using the Romi, you don't necessarily need this stuff, and you'll see us using it here without a driver station for the Romi, and we'll use a driver station for programming the FRC robot. So,
Brad, I've got a question from the chat about Romi. If
yes.
we're willing to answer. The question from the chat is if Romi is going to be supported in the future, or what that's going to look like for Romi.
Wait, say that again about. Can you
is Romi going to be supported into the future, or is it just kind of specific to this event this week?
No. Romi is going to be supported into the future. And actually, one of the original developers of this thing, this came from this cardboard robot project, is going to talk about it in just a minute. But our thought is that this is a really inexpensive platform that students and mentors could use to learn about WPI Live programming anytime they want. So you can run real-life WPI Live programs on it. You can use all the tools. And you can do everything you can do with a real robot on the smaller platform. The idea, and it was especially, we thought that it was especially relevant right now. I mean, in these days, where very often teams can't meet or students can't leave their houses. Maybe there's limited competitions. And this way, if you have an FRC robot that weighs 130 pounds and it's driving around at 15 feet per second, it doesn't work well on your kitchen table. And it's a little bit hard to learn about it. But the idea with the Romi is that it's a much smaller platform, and so you can use it anywhere. And that's sort of our aim for this. And like I said, it's especially relevant right now because somebody can just take it home with them. they can play with it and not have to worry about damaging drywall. So here's a close-up shot of it so you can see. But like I said, we're going to talk more about this in just a couple of minutes. So good question. Thanks. Keep the questions coming here. So there's instructions. There's a bunch of instructions for a lot of this stuff in the docs.wpilab.org. That's our main documentation reference. And we'll be adding, we're kind of in the process of adding more documentation pretty quickly right now for the Romi and for a lot of the other stuff that's coming up for the 2021 software release that you'll get around kickoff. Okay. So today we're using a beta version of WPI Lab. It's beta version 4, and the nice thing is that we've talked to First, and we kind of got permission so that anybody who wants it can download beta 4 because that's got the support for the Romi in it. So if you have one of these yourself, then it's possible to download software, the new release of the software, and play with it. Although we don't want you to use it on your FRC robots just yet, unless you want to be a beta team or test pilot for the software, and because it is still in beta. So we're still fixing bugs and adding things to it, but it does enable you to use the little plastic robot. So when you install this stuff, you get this installer. You double click it. This is on my Mac. This stuff, by the way, works on Windows, on Macs, and on Linux. So it's really nice. It works on all platforms. And so you start it up, and it welcomes you. And this is the beta 4 release, which is what we're making available. It asks you.
Brad, I've got another question from some of our users.
Sure.
Yeah. Where do I go to download this? If I want to work with Romi, where can I go?
Oh, we'll have some. If you go to that link at the beginning, and we'll put it up again later, then it tells you where to get this stuff. Okay, but I think it's on the blog post on wpilab.org.
Yeah.
All right, we'll make sure that it's posted in the chat here on Twitch.
Yeah, so we'll get that. Yeah. Okay, so that's maybe one of you guys who are watching can kind of post it in the chat.
Yeah. wpilab.org/blog.
Yeah, so you run the installer. It asks you whether or not you want to use the VS Code that's already there or install it again. And then you select the items that you want. So in my case, I was doing this on a new, when I captured the screenshots of this, I was doing it on a new computer, so there was no VS Code. So I installed it. It downloaded it. Then it installed all the extensions and all the other stuff that we used to make this possible. And then here we are. And then everything's ready to go. The other thing you'll have to do that's also on that page that has the links to the software is download the image for the Romi, for the Raspberry Pi that's on the Romi, and there's a micro SD card on here, and so you just have to flash it onto that. But
just to be clear, when we say image, we don't mean like your desktop wallpaper. We mean like an entire operating system that runs on the Romi.
Yes, yeah, and so we'll talk about that in a little bit. So what we want to do now is invite Joe Picordi, who actually was on the original project at Bloomberg that kind of pioneered this concept, and for using these cardboard robots with a bunch of teams that Bloomberg sponsors. They're like really generous, and they gave these small robots with Raspberry Pis to a bunch of their teams, and they did a lot of stuff with it. And then since then, this was like so exciting that we've invited them to join the control system development team, and so we've been developing software that will now work for that will now just be included for everybody. So Joe, are you there?
Yep, I'm here.
Take it away. Introduce yourself.
All right. Thank you, Brad. Hi, I'm Joe Picorni. I'm one of the developers for the cardboard robot that has now become integrated into the WPI Lib suite of functionality. I'm just going to go over a little bit upon the history of where this concept originated, how we've been working on it, why we did it, and how we got to where we are today, and then a little bit of a demo at the end. Okay. Probably messing up everything right now. Okay, so hopefully we could all see my screen right now. But we have me, myself, Joe Picorni, and ZQ Yo were some of the main developers as we went along in Bloomberg. ZQ was really the pioneer of all of this, so I want to give him credit. Unfortunately, he's not here to present any of this information, but he really led and developed and crafted out what we are going to talk about today. So he's the primary head mentor, if you will, and I've been working with him over the past 5 years on something that we called the cardboard robots. Okay, so the cardboard robots were built, and it was this competition that we would create. We had a workshop that would happen in November. Maybe some people here listening actually participated in it, but we'd have a competition in November where we invite students into Bloomberg that we would work on Saturdays. We'd have 2 or 3 Saturdays in a row. We'd pair them up with other students around the New York City area. And they would create these robots. We'd start from scratch, and we'd have them create a robot with a mentor at each individual table, similar to what the competition was going to be like in January. And that was the whole point, was to try to help prepare teams so that they were able to feel comfortable and confident that they could actually compete in the FRC challenge at the beginning of the year. So what we would do is we'd give them this kit of parts, and I'll go a little bit over that in the future, but you see this box in the lower right that would have cardboard, it would have tape, it would have markers. It was a very low budget idea because we just wanted to get as many students as we could trying things out. And what we would use is we had a A-Star controller, which leveraged Arduino for the firmware functionality that we connected to the Raspberry Pi. And we would communicate over that with some custom interface that we had for writing the code and acting as the driver station. And that would do the communication, and it would look and feel a little bit like WPI Live, and I'll show you that in a little bit. Some of the different competitions we had soccer one year, so you see that on the right with the goals, where the point was to try to push the soccer ball around and score as many goals as you could. We had dodgeball just last year. That's what you see in the upper left and in the middle. And we had a scoring system. So we'd actually mentors that were acting as referees for every single match, and they'd be counting the points. All right, so similar to what you would see in the FRC competition itself. And they were counting the points, and then once the match was over, we had a separate display system in another room that would actually show the live matches as they were going, and the ranking system and everything. And we would have a winner at the end, and we'd give them a little bit of a prize as well. So we found that they really enjoyed this, and it was a lot of fun. And I just wanted to walk into a little bit upon the cardboard robot and how that leads into the Romi. All right. So again, it was about something that was low budget, and that it was acting like what the competition would be like every year. So we developed it off of a web interface. So it was all volunteer work, and we were doing this on our own. And it was a web interface that we had that, if you look at it, it looks very similar to what you have in the FRC competition. And on the right, our scoreboard, very primitive scoreboard, but it at least kept you up to date. You have how much time is left, what the teams were, what the score was, and so on. And we even gave some tips on how to write this functionality out. One of the challenges, though, was keeping up to date with what WPI Live was putting out. They were constantly upgrading and modifying their functionality to be better, more capable, more flexible, stronger functionality. And for us to leverage that, it was a bit of a challenge. And you'll see why, or how we changed that to go with the Romi. All right. So I just wanted to do a quick example of what this competition was like. So this was last year's competition. We had an autonomous mode, and we had a teleop mode, so you'll see a little bit here.
Side ready? Good side ready?
That's ZQ, the head mentor.
Right. Rest ready? Ready. 3, 2, 1, go. Oh, yeah, stop.
All right, so you can kind of get a little bit of an idea. It's very similar, but at a much smaller scale. Again, low budget. Those barriers are just tape on the floor. But as you can hear from the laughter, it was a lot of fun. Everybody really enjoyed the days. And it was fun just to learn how to create and craft a robot, and so much fun also just for the competition. So how it all worked and was put together was we had that mock interface, that mock FRC robot code interface on the PC, and that communicated to a web service that was running on the Raspberry Pi. The Raspberry Pi communicated to the control board via I2C. And the robot code, similar to what you see in the real competition, it would run on the robot. But in order to do that, we had very primitive techniques. So everybody had their own Wi-Fi channel, and it was very, very low budget, but it worked. We had very basic hardware, like these motors were just stock hobby motors. You know, the $3 run-of-the-mill components, the wheels, wiring, everything was very low budget. Even cardboard was pretty much the boxes that it all came in. And then we found any trinkets that we found over time, we'd put it all together and get it up and running. It was pretty funny. During all this stuff, the biggest problem that we'd have is we'd run out of power. So we were constantly running downstairs. We're lucky enough to have a Home Depot right in our building. So we would run downstairs right out of the office and go into Home Depot, every couple hours and grab more batteries and bring them back up just so the kids can keep running and playing with their robots. Okay, so if we look at the kit of parts and how it was broken down, again, it was cardboard and wires for any of the robot features itself. Again, cheap plastic gear motors. We bought a lot of them because the gears would strip or wear out. The communication was done by the Raspberry Pi, and that's where the robot code was running on. It would communicate to the ASTAR32U4 as a controller board, just powered by AA batteries, which is kind of nice if you're looking at an at-home style functionality or something that you could do it yourself. Everybody has these type of batteries, and you don't have to get a big FRC battery. Just any gamepad, really, that you can leverage as a joystick. And then if you had the availability, you can leverage actuators or sensors. Although, to be completely transparent, we never built that support for those actuators and sensors. That was on our plan to do, but it was always hard to keep up with everything as it developed. So,
Joe, I've got a question from the chat about the Romi kits, if for the cardboard kits, actually. So from Dormouse in the chat, the question is, along with the source code, can we get a bill of materials to build the working chassis, Pi, interconnecting wiring, etc.? Because this idea is neat and they want to do it themselves.
Yeah, we could. One of the things that we're doing, so we're going to the Romi, and we would rather have people focus on the Romi because of some of the upgrades that I'm talking about. But as our next step this year is we actually want to go back and support this control board as well. Okay, so that'll be the next thing that we're going to develop as another target that you can download your code onto. But for now, let's focus on the Romi, and then we'll come over to this an even lower budget option. But yeah, I would say be very careful if you looked at the code that I showed. It showed sample robot, so it kind of shows how old that code actually was and how out of date we were starting to fall behind WPI Lab. So let us get it up to speed.
For those in the chat who are asking, stay tuned. We'll get that bill of materials for you very shortly.
Yeah, but for the Romi, I do have the bill of materials. We're trying to migrate that, as Brad said, we're trying to put that up on the docs area, and I'm not sure if it's up there just yet or not, but I do have a link, and maybe we could share that as well to get it for the Romi. All right, so the Romi architecture is a little bit different. What we're doing is we're leveraging the simulation option that they have inside of Romi, inside of WPI Lab. And it's really innovative. So when we were looking at how can we keep up with the WPI Lab supported functionality, how can we leverage the vast amount of complexity that's already built out and let those upgrades happen naturally, we thought, is there a way that we can just leverage the library directly itself? Okay, and one of the areas that we saw is there's this HAL simulation layer, hardware abstraction layer, that really helps us out with this actual problem. Okay, so instead of targeting the robot directly itself, it allows you to target simulations. Well, we can think of this Romi as a simulation target. All right, and the way that we thought of it that way is if we disconnect, we decouple the two sides, and we have the robot code run on your desktop, your Mac, your Linux computer, and it would communicate via WebSocket to the Raspberry Pi. All right, so we have the Pi, which is acting as a communication, transmission, translation layer to the Romi board to spin motors, to turn servos. We added some general purpose I/O pins here as well, and it allows us to interact with all that. Additionally, the board comes with a built-in IMU, inertial measuring unit. So what that allows you to do is leverage things like an accelerometer or a gyro. So it gives you a little bit more complex sensors that you can deal with. Everything's supported through WPI Lab, and that's really, really helpful for us. It's helpful for them. It's helpful for everybody, I think, and that's where a lot of this comes more together. Additionally, the cardboard is a bit flimsy, and it will only hold up for so long. This prefabricated material that comes with the Romi, the plastic chassis, and the other types of parts that you can buy to build on top of it really helps out too to keep it as a more maintainable, longer running robot. Okay, so just to kind of distinguish again, the robot code is actually running on your computer, and it would communicate via WebSocket to the Romi. All right, and that's a top-down picture of the Romi. All right, the Romi has, in addition to the motors themselves, it actually has encoders that's part of the kit of parts that we suggest. Not only is it a nice, easy way to connect the motors to the board itself, but also it gives you that opportunity to leverage the encoders on the motors so that if you need to do any type of control system or ways to determine how far things are spinning, in terms of your motor, how far it's gone, this is a really useful tool. The board is almost the same type of board, but it's embellished for the Romi itself. So it's a 32U4, the same type of A-Star controller board, but it's a little bit bigger, has a few more peripherals, as I mentioned. And it fits and it's prefabricated to fit directly onto the chassis. Also runs on AA batteries, 6 in this case, where the cardboard robot ran with 4 AA batteries. And then you need a gamepad as well to connect to your computer to move it around. And then, of course, you could buy optional sensors and actuators. On the right, I just showed here, here's an actuator that you have, a servo that you can leverage from the Pololu website. And then they also have these other types of sensors that are nice and formed already to fit onto the board as well. In this case, there's a bunch of limit switches. So these limit switches that are shown here allow you to either daisy chain them, so they can trigger that either your left, like act as a bumper. My left bumper hit, my right bumper hit, or you can look at them individually. Different ways that you can do the combinations there and really determine, give you a little bit more detectability and give you a lot of different ideas and options to have your robot perform various different tasks. The link across the bottom here is the link to the documentation as it stands today. Again, we're going to try to get this into the proper documentation so it's easier for everybody to access and develop. But as Brad said, everything's open source. So if you just wanted to go to GitHub, you can pull this down right now. All right, so getting started. So the first thing, as Brad mentioned, you have to get the installer, the beta installer. You install things down. You would push the image onto the Raspberry Pi, and then you would just do a quick configuration from a web interface for it. And then once that's up and running, you use VS Code similar to how you would use in the FRC arena. So if you develop the code for the Romi, in theory, if you're using the same generic components as you would for the robot, you could transfer that same exact code onto the robot. I can't guarantee it'll work the same because obviously the size of your robot and how it's built can have different dynamics. But the concept would be that you could actually leverage this at home, test them things out, or even in the lab, test things out and say, yep, this is kind of what we were thinking of doing, and then you could apply it to your robot as well. So I just showed here there is a example project in the WPI Live in the beta release, as Brad mentioned. That's called Romi Reference, and you could leverage that piece. And then you would just go again to your plugin, your VS Code plugin, and say simulate robot code on desktop, and you would select these two options. You can use the HailSim GUI. It's also a terrific GUI that's got a lot of different bells and whistles to it. I was using the driver station, so that's why I have the check mark here, is to use the same standard FRC driver station. And then the component that we're using is a HailSim WebSocket client. Okay, so that's the one that will allow you to connect to the Romi. That WebSocket, the question before around would we support the cardboard robot in the future? Now that it's decoupled like this, all we have to do is build the interconnection between the Raspberry Pi and that old controller board, and everything would work again the same. It would just be targeting a different controller board. All right, so as you see this WebSocket connection here in the middle, that's the really great beauty of this design, is that you actually are decoupling the two pieces. So now you can add more and more different types of hardware downstream, as long as they can access and accept the WebSocket message.
Could you share some information about that WebSocket again? We're getting some questions from chat about the WebSocket name.
Okay, so a WebSocket is just a way to communicate between the laptop and, like, I'm using a laptop, but a way to communicate between one place and another, right? It's similar to HTTP, but it's allowing more bidirectional communication. All right, so think of it as a web service if it's easier to think of that way, but technically it's a WebSocket. So a socket communication.
Gotcha. Thank you so much.
All right, and then I just wanted to show what it looks like running around the Romi. This is my 5-year-old son, and this is how much fun you would be able to have within probably 15, 20 minutes of putting everything together. Or maybe about an hour building the hardware out too. All right, so that's all I had for today.
I do have another question for you, if you're willing to answer it. So from MR Squared in the chat, does Romi support advanced programming like drive characterization and trajectories, or do we need better sensors for those?
I'm sorry, which
we're looking at doing drive characterization and trajectory.
I don't believe that we support those just yet. I'd have to see how those would decompose into the underneath WPI Live. But okay. I'm not 100% certain. But yeah, I mean, whichever ones, I guess, would be good that, you know, we can kind of compile a list and make sure that we put those as priorities to support in the future.
That's awesome. Thank you so much.
Yeah. Are there any other questions? Or are we good to go back to Brad and Grant?
It looks like from the chat we are good to head back to Brad and Grant.
Okay.
Thank you.
All right. Hey, thanks, Joe. That was awesome. This is actually really exciting. To have a little small robot, and I think based on the questions in the chat, I think you guys are pretty excited about it too. One of the things that were a couple of interesting things about this. A lot of you guys are asking questions about how you can get one of these or how you can get going. Stay tuned. Wait a couple of days. We're kind of in the middle. We have two things going on. One of them is the Romi that was separate from doing the Hour of Code broadcast. We expect in a couple of days we'll have more information about how you can get a Romi from Pololu pretty inexpensively. And in fact, they're putting a first Romi product onto their product pages, so you can just order it. And we'll have a coupon for first teams so you can get it discounted. So that's something that's coming up. So you'll be able to get the Romi from Pololu, and there's a few other parts that you'll have to get, like the Raspberry Pi and an SD card to stick on top of it, and we'll have links about where to get that from Amazon. But the idea is that the whole thing together will be about $140 between the Raspberry Pi and the SD card and the Romi and all the stuff that Joe just talked about. So this platform, this whole platform will be about that cost. So that's that, and so coming soon, we're like within days of having this all finalized. So So hang on for that. And then the other question about the characterization stuff. For the characterization tools to work, you need IMU and you need wheel encoders,
yeah.
and this has both of those. We'll play with that, and you might ask a little bit later in the talk, either Pratik or Tyler, when they're talking about some of that stuff, some of the advanced stuff, particularly Tyler at the end, about using some of those tools and using some of the path planning stuff with the Romi. But I expect that that's something that we can get to work if it's not already working. Okay, so what we're going to do, well, okay, so before we go further, so we're going to show you the Romi right now. We're going to show you some things you can do with it and how you can program it. But a lot of you guys are maybe not real experienced at doing robot programming for first, and you're kind of at home, and it's and you want to learn more about this. And what's coming up really soon is through the First at Home program, there's curriculum being developed for the Romi. So you'll be able to go and do some online classes about how to do that. And for that, we have Lori Birch, who's in charge of all that stuff, who's going to talk a little bit now about how that's going to work. So Lori, thanks.
Thanks, Brad. So for those of you that don't know me, my name is Lori Birch, and I'm based out of Colorado. I joined First a little over a year ago, and I'm formerly an FRC and FTC coach. So I coached FRC for 6 years before I switched to FTC, because I taught in a very small rural school district in Colorado, and FTC became a better fit for us. So part of my job in this as a manager of digital instruction is really to provide resources for teams to be able to do this in a way that it kind of coordinates with the education that they might already know. And so what I'm working on doing is really developing an at-home project that you can do with the Romi robots. So I'm working on developing a scenario for a game that you can do on your own, that you could do individually at home, or you might be able to pair with another team or two teams and make this your own game. And then leading you through that process of, okay, how do I really take a little bit deeper dive into understanding the hardware and the software, and then how do you design code around that and really decompose and use computational thinking in decomposition and abstraction, pattern recognition, and really understanding these details of the Romi robot, so that when you come out of programming it, you have a better understanding of how does this really relate to an FRC robot, and then how can I do this at home? So that's really our goal within the education department at First, which is what I'm part of, is to provide you with those resources to make this a little bit easier, and kind of scaffolding that information in a way that you might be able to dive into those details and correlate it to some of the other things that you're learning. And we look forward to producing those for you. Hopefully they will be out sometime in January, so you'll have to look at our First at Home page and stay tuned to team updates and the marketing emails that you'll get that will give you that information.
All right. Hey, thanks, Lori. Oh, am I?
We're good.
Okay, thanks, Lori. That was great. And I'm really looking forward to seeing a lot of the stuff that you're coming up with. And I think the teams are really going to appreciate that. Really get a good, spend this time getting a good head start in doing robot programming. So then it's particularly relevant right now, during this Hour of Code week. And so that's pretty awesome. Okay.
And those lessons will be all free on the First at Home webpage when they come out. So.
Okay. Yeah, so everybody kind of keep an eye on that. And all this stuff is going to be showing up really soon. And I'm sure there'll be more blog posts and other information about it coming out as this stuff gets released. So what we're going to do now is we're going to write a program for the Romi, so you can kind of just see how to do it. And actually, I'm going to let Grant write the program. I'll talk about it.
Let's go.
Because he's much better at this than me. So the idea here is I kind of borrowed this from some VEX course that I saw somewhere. But we're not going to talk about that anymore. But the idea is that we want the robot to start at position 1 here, and then get over to position 2 without crossing any lines. So Grant is going to show this. I guess we can get a close-up shot here of Grant doing this. Wait. All right. Oh, there it is. So what's happening is that the robot's going to start here, and it's going to drive forward, and then turn with sound effects. Okay.
The sound effects are necessary.
Okay. And then drive there, and then turn again. Turn there, and then come back, and then park in over here. So that's what we're going for, and so we're going to write a program that does all that stuff.
That was really exciting.
That was exciting. That was, and I, it was, it was like really exciting, especially with the sound effects.
Of course.
So what we want to do, and by the way, I just want to point this out. Have this little roll of tape. Some of you guys have been noticing that sitting here. It's really important with just like you do with FRC robots, or any robots, when you're testing them and working on the code, to keep it blocked so that it doesn't if you have some problem with the robot or some problem with the program or something, the robot doesn't launch, and fly off the table, because that would kind of ruin your day. So that's what the roll of tape is for. Okay. So that's what we're going for this sample program, and so we're going to use a technique called command-based programming for writing this thing. And the idea is, and by the way, just to make it clear, I think I said it before, but I just want to make sure everybody understands that programming the Romi uses exactly the same tools and exactly the same libraries that you use for programming your FRC robots. And so everything that you see here that we're doing with the Romi, Grant will continue to do with the FRC robot that we got here, the little desktop FRC robot, and then we're going to and just use the same libraries and the same stuff. So we're not showing you super secret special Romi programming. We're just showing you the regular stuff that you'd use for your FRC robots. So what is this command-based programming stuff all about? Well, it's kind of a method that we came up with a long time ago, a bunch of years ago, because one of the things that we noticed was that we would go to a competition and see teams, and they'd be writing their robot programs, and it was really hard to figure out, they're maybe new to this object-oriented programming stuff, with Java and C++, and maybe they didn't know how to organize the program. And so this was a really nice way of structuring programs so that they had a lot of really good characteristics, like that they were easy to write, they're easy to extend, they're really easy to debug and test, and you get good code reuse. So you can do stuff over and over again. And I got some good stories about some of this code reuse stuff that's really interesting. So the way this works is that when you create a robot project, and we'll do that. Grant is going to write something from scratch here. And by the way, I will say, we are taking a tremendous chance doing this live and hoping that we get everything
it's gonna
right
work perfectly
on camera.
Okay,
this is very risky. Whenever I do this, and I'm doing a class or something, and I do this live stuff, it usually works, but then sometimes I forget something or something like that, and then it's pressure. I'm under the lights. There's all this pressure. But anyway, we'll see what we can do. So when you create a robot project, you get a bunch of files, and one of them is called main. And that's the thing that kind of launches your robot program. There's another thing called robot.java. That's this, and there's corresponding files for C++. So there's robot.java, and that's the part of the thing that kind of controls the flow of the program. And you'll see that in a little bit. And then there's this other file called robot container, and that's where we create a lot of this stuff that we're going to use. A lot of these classes and other things that we're going to use for writing our robot program. And then we have robot container. We have constants. There's a constants.java file, and inside of there are all these kind of global constants, like port numbers and things like that sensors are plugged into and that motors are plugged into. And so we keep it there so it's actually really nice that it's there, because then when you're ready to wire a robot, you can just print out that file and hand it to the guys who are doing the wiring, and they'll know what things are supposed to be connected to what. So that's kind of nice. So the robot.java file kind of looks like this. It's got a bunch of these methods in it. There's this robot init method, which creates one of these robot containers. There's a robot period. The way this stuff works is that about every 20 milliseconds, there are these periodic methods, these periodic functions that keep getting called in your robot program. And so you kind of advance the robot a little bit, make it do a little bit more stuff, get a little bit further in whatever it's doing, its autonomous routine, or you read the joysticks and then send stuff to the motors. And that happens like, kind of every 20 milliseconds. That's 20 thousandths of a second. So there's this robot periodic function here, or method, and that's scheduling these commands that we're going to talk about a little bit. And that happens each time this loop happens. There's some stuff here for initializing your autonomous program. There's some stuff for initializing your the teleop program that you have. So when you switch modes between autonomous and teleop, then those initialize. And there's a bunch of other methods that are like that you'll see. But generally speaking, you don't have to do anything to the robot.java file. That pretty much has very, very few changes that you might have to make to it. The robot container is where you're creating all of these subsystems and commands that we're going to talk about that are the basis of command-based programming. And so here's some examples of that. There's a function here where you might configure button bindings. So if you have a joystick with a bunch of buttons on it and you want it to control different functions on the robot, you might put that there. And there's another function here that gets the autonomous command. And you may be getting that through a dashboard, so you can pick one of many autonomous programs to run depending on maybe who you're playing with or what side of the field you're on, or which position you're starting on, or any of that kind of stuff. The fundamental thing with one of the fundamental things with command-based programming is that the idea is you want to break up your robot program into the subsystems that are on the robot. That's like a really good way of breaking up the program and structuring it so it's really easy to find things. And it keeps all the stuff together for each subsystem. So in this case, this is the little FRC robot we're going to be demoing a little bit later. And it's got a drive base, and it's got a chassis, and it's got an arm, and it's got a gripper on the end. It's a little bit hard to see. This is in my office. It's like loaded with robots and stuff. So it's a little cluttered. But anyway, so that's the robot we're going to use a little bit later today. So subsystems represent an encapsulation of all the code you need to operate a particular robot subsystem. So like arms, drivetrains, elevators, grippers, that kind of stuff. So all those things where you'd point to it and say, oh, that's the elevator subsystem, and that's the arm, and that's the chassis. All of those things are separate subsystems. And you would create these subsystems that do that. And you'll see how to do that in just a minute. It's pretty easy. The nice thing about this is this implements, as you learn more about computer science and you take more classes, there's this thing called the single responsibility principle. And the whole idea is that you want each of these classes that you write to only do one thing, to only be concerned with one thing in your program. So you don't want to write a single class that does the arm and does the chassis and does something else, because it just makes it hard to modify. If the different functions for all of these pieces of the robot are spread throughout the whole program. So the idea is each subsystem just controls its subsystem. And that's kind of how this works. So here's kind of an example. Here's a subsystem, an example subsystem, and it's got this periodic method. So fundamentally, all the subsystems have this. So again, every 20 milliseconds, this periodic function is called. But you really want to add more stuff to your subsystem to make it real. So here's like a more real subsystem. This is the hatch subsystem for some FRC robot that may want to pick up hatches and put them somewhere. And so, it's got some sensors in it, like these double solenoids. And you put those inside the subsystem because you want the subsystem to be the thing that knows about the actuators and the sensors and all that kind of stuff that go with the subsystem. And then you put in some methods, some functions in the subsystem that can operate it. So like grab hatch and release hatch are two functions, two operations that the subsystem can do. So you just put that stuff into the subsystem. Now it's not actually the code that does the whole this big long process. It's just the stuff that gets the hatch solenoid going in the right direction in this case. So it either makes it go forward or makes it go reverse, so that the pneumatic system that's doing this goes in or goes out. And So that's the idea, that all the stuff to control the subsystem is in the subsystem class. So we're going to write a chassis subsystem for the Romi, and by we, I mean Grant.
Yeah.
And I'm going to heckle while he's doing this. So what we're going to do is switch from the presentation and go over to VS Code, which is right here.
Excellent.
And then we're going to switch places and see what happens.
Thank you, Brad. Okay, so we're starting off with a completely blank slate. We have no project made, so we're going to do that first. So we're going to type create a new project. And here we are. So we're going to not choose an example. We're going to choose a template. We're going to do a Java project here. And finally, we're going to do a command-based robot. So this is what you might want to have. We're going to select a project folder. I am just going to do, I'm just going to do Brad's main folder. Sorry, Brad. And we're going to select that. And then we're going to enter a project name. And we're going to call this Romi Demo. And of course, because I'm a Team 190 mentor, has to be Team 190 here. So we're just creating a blank project here. And we're going to click Generate. And we're going to say, keep it in the current window. Yes, please. So we generated a bunch of stuff. You can see some files, some directories on the left. At the bottom, we just built the project. Basically, it just compiles, makes sure that the code that was automatically generated is proper code. And it is. It says build successful. So we're going to open this up. We're going to open up our project. We can see these files that Brad described earlier. We have constants, we have main, we have robot container. And the first thing we're going to do is, because we're making a Romi project, is we're going to go into our build.gradle. And there's just one little thing you have to do. So we scroll down here, and we have to choose whether we are a server or a client. And when you're working on just one of these little Romis, these little robots, we use the client. So we're just going to uncomment that. Excellent. So that's all you need to do here. And you just close it out. And then we can start working on our first subsystem.
Okay, you got the, okay.
So we already have this example subsystem, but we're going to create a chassis subsystem, because all we have on our Romi is essentially just two motors controlling our wheels. So I'm going to right click, and I'm going to do create new class command. And I'm going to type command. We're going to create what's called a new command. And we're going to name it chassis. So this gets created. Excellent. And we have a whole bunch of blank methods that we can now implement. Oh, I'm sorry. I made a command by mistake. I'm trying to make a subsystem. That's my mistake. So we're just going to delete it. And we're going to create an actual subsystem, not a command. Caught up in the moment. New subsystem called chassis. Excellent. So we have these blank methods that we were talking about. Now, what we have to do is we have to create a bunch of references to our motors and to our encoders that we are going to be using. However, we have to know where these ports are that we physically plugged in. So we're going to go over to our constants file, and we're going to make a whole bunch of constants here. So you'll have to give me a moment, but these are going to be the same exact constants that you would use when we are making our own robots at home. So we are just defining a bunch of integers that refer to ports. So the first one I'm going to do is we're going to do left motor port, and the default is 0. Hold on. We're going to make the text bigger so people can see. Do you know how?
Maybe the editor, preferences editor.
How about?
So code. Let's see.
Oh,
code,
we could do code.
Preferences. Editor. Settings.
Settings, perhaps.
And then editor.
Oh, yeah, there we go. Controls a number of lines.
Oh, wait, command. Wait, just hold on a second. What is it?
Command plus.
Command plus.
In the editor, I think.
Okay, go to the editor, hit command plus.
Oh, let's go.
Sweet.
Thank you.
Thanks, Yoni.
Yeah, we have another WPI Lib developer on staff here to help us out. So hopefully it is big enough for people in the chat to read. Sorry, everyone. So again, we're just making a list of motor ports. So write motor port equals 1. And then from now on, I'm just going to copy all this so I don't have to type it every time. This is, as you know, it takes a little bit to type all these out, but that's okay. So the next thing we're going to be doing is we're going to be doing our encoder ports. So we have on our Romi what are called quadrature encoders, which means not only can we see how far they are spinning, but we can see what direction. So in order to get direction, there's actually 2 ports it plugs into. So we're going to name them left encoder A and left encoder B. And then we're also going to do this for the right side as well, of course, because we have encoders on the right and we have encoders on the left, and we're going to use both. Cool. Okay, so now we have all the encoder ports. And the last things we're going to do is for some constants that we're going to use later. So we have to navigate this maze. Brad discussed this earlier, and I showed off the robot moving through this maze. The way that I think we should do it, and the way I'm going to do it, is we're going to tell it to drive like 13 inches forward, then turn left 90 degrees, and then drive 12 inches forward. And my key is I'm telling it to drive inches. So in order to get it to drive inches, I have to convert these magical encoder units that we get out of our encoders into real-world units. So with that being established, we're going to define some more constants that we're going to use. So the first one we're going to do is we're going to do our wheel diameter. Okay, and if I wanted to, I could get out a tape measure, and it would be equal to exactly 2.83 inches. Our next one is going to be one that relates to how our wheel rotations reflect in encoder units. So this one is going to be called pulses per revolution. So this is essentially how many encoder units there are in one full rotation of the wheel. What we have next is we have to convert directly from pulses to inches. So that's what inches per pulse means. And this one is, math.pi times our wheel diameter divided by our pulses per revolution. So that is the amount of inches per pulse. So we'll be able to use that when we enter in how many inches we want our Romi to drive. We can figure out how far our encoder needs to be spun. And then also we have some turning that we're going to be doing later, because we have to turn to go through our maze. So we're going to have 2 more variables. We're going to have one that is the width of our wheel base, and this is called wheel track for us robotics folk. And then we have one more variable, which is relating the amount of inches that the wheel needs to travel to the amount of degrees that the robot has to turn. So we have inches per degree. And that equals, this is our last one, by the way, and then we'll start getting into some more cooler stuff than just defining constants. All right.
And I'll just say what that last thing was is if you think about it, when the robot wants to turn, one wheel is going to go one way, the other wheel is going to go the other way, and it will turn in place. And so you can imagine, and because the wheels are on the center of the robot, then it's going to turn around about the center of the chassis. And so what we're doing is defining how many inches of travel the wheels have to make like a full revolution around this circle. So if you know the wheel track, then you can, that defines the diameter of a circle that the robot turns on, and so if you know the circumference of the circle and you know how far the wheels, how to get the wheels to turn, but for some distance, then you can compute that constant and get the inches per degree. wheel motion inches to degrees of robot rotation.
Okay. Thank you for that, Brad. We are now going to go to our chassis because we have all the constants we need to start doing some actual work. So I'm just going to delete this default comment. And now what we're going to do is we're going to start making some references to our motors. So the type of motor that we are going to use is called a PWM Victor SPX. Now this is not the actual speed controller that's on the robot. However, you interface with it exactly the same on a low level, so it'll suffice. So what we're going to do is we're going to make a left motor and we're going to make a right motor. We are also going to define our encoders. So we have encoders. We're going to do a left encoder and a right encoder. And the last thing we're going to do is we're going to create what's called a differential drive. So a differential drive is just our way to access a bunch of really useful methods like it's called arcade drive or tank drive. Basically, you can tell it how fast to go and what heading, and it will talk to these motors and it will tell it to drive at those speeds. So it's just a really useful class for driving, and you should definitely use this on your real robots. And we're going to call it differential drive. Now,
I've got a question from the chat for the folks following along at home, if that's okay.
In our actual constructor, we have to initialize our motors. So our left motor.
Question?
Oh, we have a question.
We have a question.
What's up?
We did. Well, so I had a question as you were moving between topics that was just my own, and I figured I wasn't going to ask it because we'll let you guys teach the folks in chat. But we did also get a question in chat specifically about the constant. So when you described it being a sort of like, we'll move on to cooler stuff. One of the folks in chat is interested in some more information about the constants, just what
Sure.
what your constants are, but also maybe for the folks at home who might be super new, kind of describe the difference a little bit as you tab back to show it to them for the moment.
Okay. So this is our constants file. So each, like, I'm sorry, what was the question about the constants?
So
Brad will take
let
over.
me take a shot at
They
this.
just wanted to see what they were.
Okay.
But the I guess the structure around why would we tab back to it is, why are those things so important as we build this code?
Oh, good question. That's actually a good
Yeah,
question.
that's a good question.
So here's the thing, and that when you throughout the program, you're going to want to do things like you're going to say, you want to know which ports things are plugged into, because you want to be able to create these devices that are that correspond to particular ports on the robot controller. I mean, not so much for the Romi because it's pretty fixed, but for an FRC controller, there's lots and lots of ports you can plug motors and sensors into. And so by putting all that stuff in one place, then you can refer to it by name rather than referring to it by number.
Yes.
And it's all in one spot. So when people, if they want to change something, or say you're in a competition and this arm comes in and grabs all the wires from your Robo Rio and rips them out of the Robo Rio, and you got to put them back in a hurry before your next match. The idea is if you look at the constants file, it will say where everything is plugged in. And so we're just referring to these things with what's called, we're referring to them symbolically. In other words, we're using these names for the things rather than using the numbers throughout the program. And so if we want to change it, we only have to change it in one place, and that's in this constants file. The other thing I'm going to mention was that looked kind of magical, all that stuff that Grant just did, like where all those numbers came from and everything. But good news, there's sample projects for the Romi with VS Code. When you install the WPI Lab software, you can create a sample Romi project, which actually includes code to drive the chassis, and it includes all these constants, so they're already there. So you don't have to remember them or be scribbling them down. And,
you don't need
stuff,
to be remembering
because
every
all the
number.
Romis are the same. So so all these basic constants for the stuff that's built in will be part of some sample projects that you can use when you create Romi projects, and so you can start from there.
Yeah.
Libby, does that answer? You think?
Thanks so much, guys.
Does that do it? Okay.
Excellent.
Yeah,
So
I
Grant.
think one of the things that I think is so important this week with Computer Science Education Week and the Hour of Code, right, is making sure that we see that coding's for everyone. So thank you for rewinding a little bit so that our folks at home in the chat can understand. We really appreciate it.
Sure.
No, you know what? And for you guys, sometimes, like we've been, so I've been teaching college courses, and Grant's,
I'm a college
has
student.
been doing this for a while, and so it's easy for us to forget. And so if you guys who don't have a lot of experience and want to know more about this, just interrupt us, and we're happy to stop and explain anything. And also,
Easily. I promise I will.
okay, thank you. And also, don't forget that when you do the first at home classes that Lori talked about, it's going to be going at a much slower pace, and probably and then you can back it up and then go forward and that kind of stuff. And there's lots of documentation that you can look at even for this stuff.
There are tons of resources for you
yeah,
guys.
so lots and lots of resources. We'll talk more about some of those later. All right.
Cool.
Good.
Okay.
Okay, Grant, carry on.
All right. So yeah, we have the encoder. We have these constants just because there's nothing worse than trying to remember what this random number means in your chassis class. So instead, we use something with a name. Okay, so where we were constructing all of our different variables that we have, all these different attributes that relate to our chassis. So the first thing we're going to do is our left motor. So what we have to do is we have to pass it a port number. And we just defined all of our port numbers in our constants file. So we just import constants, and we do constants.left motor port. Easy as that. And now we have access to our left motor. What's it mad about? What is it mad about?
It didn't do the, oh, it did do it.
It did. Hold on.
Did you spell it right?
I thought I spelled it right. What is it mad about?
I don't know. So, do the next one and see what it
Okay,
does.
we're going to do the next one, and we'll come back to that issue later. So we're going to define our right motor the same exact way. And we are going to give it constants dot right motor port. Oh. So my issue is, if I look very carefully, I've actually spelled the name of this wrong. So instead of PWM Victor SPX,
No, it's spelled right.
What?
Go back. Just go back.
What?
So when you do this,
Chat's
you have
also
to
saying you need new.
What?
Chat's saying that it needs new.
Yes, that's
for the
I'm being so silly.
That's what I was pointing to.
I thought you were I am being so silly. I do this professionally, and even I forget the word new sometimes. So don't worry, guys, if you make silly mistakes like me. It's okay. I forgive myself. We're going to make a new differential drive. I actually said new this time. Pretty smart of me, I know. And we just create it using the left motor and the right motor. Oops.
And thanks to the chat.
Yeah, thank you, chat. You legit, have saved me. Okay, so we construct our differential drive, and we're also going to construct our left and right encoders. So because these are quadrature encoders, like I said, we need to include both the left encoder A and our left encoder B. Lovely. And then we also have to do our right encoder as well, because we have left and right sides of the robot. And we're going to do the same exact thing that we just did. We're going to do right encoder A, and we're going to do constants.right encoder B. So now we've actually constructed all of the hardware objects inside of our chassis subsystem. The last part we're going to do is we have to do some configuration on our encoders. You remember in our constants class, we defined all these magic numbers using math.pi that relates to the amount of inches that our wheel rotates versus the amount of encoder units that is in a single inch. So what we're going to do is we're going to do left encoder dot set distance per pulse. So that way we can do left encoder dot get distance and know how much our chassis has moved. Pretty nice function that we have already just built into the library. So to do this, we do constants dot inches per pulse. There we go. Okay, and we're going to do the same exact thing with our right encoder. We're going to do set distance per pulse constants dot inches per pulse. Cool. And now the last part we're going to do is later we're going to do some just easy testing of our Romi. We're going to move some sliders up and down, and the Romi is literally going to move. So to do that, we are going to add what's called a child. I'm going to call this one the left encoder, and we'll see this on our smart dashboard, or on our simulator GUI, excuse me. So if we add child, we give it a name, and we give access to it. I know I haven't explained this great, but we'll see what this does in just a bit. So we add children for both encoders. Cool. So now we've set up the base class for our chassis. That's all we have to do. Of course, I actually did forget one little thing. So we are going to actually make sure that our motors both drive forwards when we tell the robot to drive forwards. So in order to do that, we have to set the right side of our robot to be reversed. So that's what we're going to do here. And then also with our Romi, there's a little quirk where while it's running, sometimes it gives warnings about loops running too long in the low-level WPI lib. And it says like, oh, warning, you know, it's not updating fast enough. So we are just going to tell it to turn off these safety warnings. I promise it's a little robot. It's not going to hurt anyone. So it's okay to turn off these safety warnings. So this is actually the end of our chassis class. Now what we're going to do is we are going to start writing commands to start solving our maze. So we're going to come over to our commands, and we're going to create a new command that's called forward. So this is whenever we want to drive forward, we are going to use one of these commands. And there we are. We're in a base forward class, and we're going to fill it in with some information. So the first thing we want to do is when I create a new forward command, I want to tell it how many inches I want the robot to drive. So to do that, I'm going to pass it a parameter called double inches. Okay? And then I want to save this throughout the program. So what I'm going to do is I'm going to make a new field called double distance. So inside our constructor, that's what this method is called, we're going to say distance equals inches. So that way I can use this value later. Also, because we're defining a command, we have to tell the command what sort of subsystems it will be modifying. So because this is a driving command, we actually need to use our chassis. So I'm going to create a chassis object because I am going to use it multiple times. And I have to say chassis equals and then the reference to our chassis. However, we haven't actually created a chassis yet. So to do this, we go over to our robot container. And you can see we have example subsystems and commands already made. We're going to just delete those because they don't actually reference any real hardware. And instead, we're going to make a public static final chassis named chassis. And it's going to be equal to a new chassis. Great. So if I save it, now I go back over to forward.java, and here I say chassis equals robot container dot chassis. So now we'll be able to access this chassis throughout the class. And of course, it requires the use of the chassis. So we're going to say add requirements chassis. So now no other command can use this chassis at the same time. We are driving forward, and we can't be turning at the same time we drive forward. So we have the rest of the
Can I
commands.
pass a question along from the chat for you guys as well?
Yes.
Yeah, so you guys talked about adding something as a child, and from Firsty4786 in the chat, we've got, what does add child do? What does that process mean?
Okay, So add child, what it does is it takes the values from our encoder and it puts it on our dashboard. So when we're running a robot program, it comes up with whatever dashboard we choose. Here we're going to be using Smart Dashboard just for our own convenience, and it will be showing the values of the encoders. It's also going to show on the simulation GUI. So when we run the Romi, it'll come up with this pretty purple and black GUI. It will show the values to the encoders as well. Is that correct, Brad?
Pretty much. And so that makes it available for the dashboard, so you can see what's going on with those. And you can, when you're testing them, you can see what's happening, and you can look at the values for those things. And wait, when you finish, why don't you go and finish the command? Then we'll talk a little bit more about how commands work.
Okay, cool. So back in the forward command, do we have it out? Yes. Okay. So the first thing we want to do is when we create a new command and we tell it to start, the first thing that's run is called the initialize method. This is run immediately after the command is told to start. And what I want to do here is I want to set all the encoders to 0, so that way when I tell it to drive 13 inches in one direction, I want it to start from 0, so that way we only have to go to 13. We're not starting from some other number and have to worry about all that. So what I'm going to do is I'm going to do chassis.reset. However, I haven't actually defined this reset method yet, which is, an issue. So what we're going to do is I'm going to do command plus, and I'm going to do create method reset and type chassis. And I'm going to go back to chassis and scroll to the bottom, and wow, there it is. So I'm going to give it a body now. So what I wanted to do earlier, I said, was I want to reset the values of my encoders. So I'm going to do left encoder dot reset, and I'm going to do right encoder dot reset. So that's all that I wanted this to do. And I save it, and it's good to go. Going back to our command, we want to go to the next method. This method is called execute. And what I want it to do is, while this command is running, I want it to be driving forwards. That's in the name. So I'm going to do chassis dot drive, and I'm going to give it some values. And we're going to talk about what these values are right now. So we haven't defined this method, just like the last one. So we're going to right-click on, we're going to do create method. And we're going to come over here. I'm going to scroll to the bottom. Actually created it a little wrong. So we're going to make a drive method. And I want the first parameter to be speed. And I want the second parameter to be direction. And then we're going to use our differential drive class that I talked about earlier. And we're going to tell it to differential drive.arcadeDrive with our speed and with our direction that we just gave it. And then we're going to save. And we'll go back to our forward class. So now we're driving at 15% speed straight forwards. So that's what those numbers meant. Going to our next method now. And please, if you have any questions about what I'm writing, send it in the chat and we'll get interrupted. In our end method, when it's done driving, I want it to stop. I want it to stop driving. I want the motors to turn off. So we're going to do the same thing that we've been doing. We're going to create a new stop method. We're going to go back to our chassis. And we're going to call our drive method that we just defined. I'm going to do it at 0 speed and 0 direction. So when we call our stop method, our chassis stops moving. And now the last part, you might have realized the flaw that we have yet to acknowledge is we haven't told it how far to drive. We saved this value distance, but we haven't used it. So that's where it comes in is finished. So every 20 milliseconds when a command is running, is finished is called, and if is finished returns a value that's equivalent to true, then the command will die. So what we're going to do is we're going to do chassis dot get left distance is greater than or equal to distance. So what I'm going to do is I'm going to make a method here that returns the amount of distance the left side of the chassis has traveled. The left and right should be the same because we're driving straight forwards. So we can just grab the left, or we could have grabbed the right. It doesn't matter. So we're going to see if the left distance is greater than or equal to our intended distance, then we'll stop the program. So we're going to create this method, going over to chassis. And get left distance is going to do left encoder.get distance. Excellent. So now we've actually finished our forward command. And did you want to talk about something now?
Well, yeah, let's talk about commands a little bit. Since Grant just wrote a command here that does something, let's talk a little bit about how they work real quickly, and then come back and we'll try this to see if it works. Just so maybe it makes it a little bit easier to understand what he was doing. So, we did this. We talked about writing the chassis subsystem, and now we're going to talk a little bit about commands. And what happens with commands it's kind of interesting. The idea is that when you want to get the robot to move or do something over time, this is where commands come in. And so these are actions that the robot does that that use the subsystem methods. And they're really like, if you've ever heard of state machines, the commands correspond to states inside of a state machine. So when a command starts up, it initializes itself, and then continuously it executes, checks to see if it's finished, and it does that over and over again every 20 milliseconds. And then when the like Grant said, when the isFinished method is true, then it calls its end method. So it gets to clean up, like in this case, maybe stop the motors from running. So that's sort of what those functions were that he was filling out. So commands can either start at the beginning of the autonomous period, so you can make it so that the robot.java project, the robot.java file will automatically start an autonomous command when the autonomous period is entered. You can manually start them by calling the scheduler from a program. You can have default commands, and we'll see that a little bit, that are tied to a subsystem, and they'll run when no other commands are using that subsystem. You can trigger commands with a button on a joystick or something, and you can start them when you press a button on the dashboard. And actually, we'll do that with we'll set that up for the forward command. So we have to remember to put that in when we get back. And then commands stop when the finish condition is met. In other words, when the isFinished method returns true. And you know how Grant said which subsystems the command was using? In this case, the forward command was using the chassis subsystem. The whole idea of commands is that they work on a particular set of subsystems. And so say you're telling the robot to go forward because you press the forward button on your joystick. But then you said, oh, no, I really wanted to go backwards. And then you press the backwards button on the joystick. Well, you can't have the wheels trying to go forwards and backwards at the same time. So what happens is that when you start a second command that uses the same subsystem, so forwards would use the chassis, backwards would use the chassis. So the forward command is running, hit the backwards button. The backwards command tries to start, and it's using the chassis, so automatically the forward command stops, and then the backward command starts going. So you don't have this conflict problem that we were just talking about. And so if that happens, the forward command would be interrupted, and so the end method would be called with this flag set that says it was interrupted. So you can do something special if you want, if the command was interrupted. So Grant just showed you a command, so I won't go through this. This is kind of a sample of what it looks like. So that's kind of the idea. And a little bit, there's another thing. Well, we'll wait. We'll try these commands first, then we'll come back and talk about command groups. So we can try this. You can add something for the dashboard. Why don't you take over, Grant?
Yeah, let's do that.
And add something to robot container so that it shows up on the dashboard.
Okay. So we have some error here. I just wanted to address that. So we have this get autonomous command that seems to be a little angry. So we're just going to write in a filler for now, just so it stops being mad. It's just going to print the word message if we enable it in autonomous. So just ignore that. Here, we're going to make a new button on our dashboard that when we click on it, it runs our forwards command. And so what we're going to do is we're going to do smart dashboard dot put data. We're going to give it a name. We're going to call it forward. And we're going to use the value of a new forward and we're going to make it drive 10 inches forwards. And do we want to try this now?
Yeah, well, yeah, once it's all there, we'll try
Oh,
it.
okay. So we'll
Yeah.
do some more.
I mean,
oh.
is this, you think
I mean,
we're done?
yeah, we click the button and it will go.
All right, let's see if we can, well, we have to put it into the robot.
Okay, so the first thing we got to do, we are connected to our robot, I believe. Yes, we are connected to our robot. So what we can do is we can click on the WPI Lab at the top, and we can type simulate robot code on desktop. And you'll give it a second to think. It's going to compile our code. It's going to give us some options. You can set the defaults here, but for now we're just going to click all three. And I'm going to click OK. And it's going to think about it. It's going to set it up. It's going to run some stuff. And we're brought over to this other page. So this is our robot simulation GUI. And what I'm going to do is we are going to enable it in
Teleop?
We're going to enable in Teleop. Okay? And then, do you know where your shuffleboard is?
Okay, just go back and just run, you can run
Okay,
the tools.
we'll run a...
Start tool.
So we're going to start a new tool.
And
we're
do
going to
Smart
start
Dashboard.
our smart dashboard. So here it is. Here's our smart dashboard. We're going to ignore these four for now. This is like remnants of a previous program. But we're going to just look at this bottom one. So I'm going to drag it over. Oop. Sorry. Hi. We have a question?
Oh.
Or is not full screen? What?
I think we're okay. There were some questions about the materials being available on the WPI Lab site. So we got the link posted in chat to where the
good.
information from today's session will be. All the code used, the slides, anything else that folks are looking for are going to be on the link that's posted in the chat.
Okay.
Okay, good.
So we've enabled it in the teleoperated mode, and we have this button that we just defined. And if we click on it, it doesn't do anything. What the heck?
Is it, it's in Teleop?
It is in teleop mode.
Yeah, this thing's been, we may want to change the batteries in here because it's been sitting around for like a half hour or 45 minutes while we've been talking.
It's been on the entire time we've been here.
All right, so we'll do that. Why don't you go and
Okay.
do another
right.
command?
So anyway, this is the proper way to do it. I think our Romi may be low on batteries. We'll see. But we'll just go back to our code. So we have now implemented our driving forward code. We will test later, once we change the batteries, that this works. But in the meantime, what we can do is we have driving straight. Next, we have to have turning. So we are going to now define our own turning class, our own turning command. So we're going to do create new command, and we're going to do a new command, and we're going to name this one turn. Okay. So again, we have a completely blank command. I'm going to get rid of this just so it's more clear for you guys. And I'm going to delete this comment, and then we'll start writing again. So the first thing we're going to do is we are going to access our chassis. So I'm going to make a chassis field that we're going to use again later. We are also going to define some other fields. This one is turn inches. This relates to, again, our turning in place, so how much our wheels need to turn in order to turn the inputted amount of degrees. That's what this variable means. And then our double direction is going to be the actual direction that we are going to be turning. So if I say 90 degrees, I want it turning to the right. Or, sorry, if I say 90 degrees, I want it turning to the left. If I say negative 90 degrees, I want it turning to the right. And that's what this variable is going to store. So in our constructor, we're going to ask it to provide us an angle. We're going to now save our chassis just like we did last time by doing chassis equals robotcontainer.chassis. And then we're going to add requirements. We're going to require our chassis because we will be modifying variables within it. We are going to tell motors to spin. Next, we are going to assign a value to our inches variable. So we're doing some funky math that Brad may want to explain because I'm not super positive on how it all works. But what we do is we take the absolute value of the angle, so like the magnitude of our angle, we multiply it by pi, and we multiply it by our constants dot wheel track, and then we divide it by 360.
Do you want me to explain it?
That would be good, thank you.
Okay, so what that's doing is, if you look at it, the last part of it where it says wheel track over 360, so the wheel track is, or pi times the wheel track over 360. So the wheel track would be the diameter of the circle that the robot turns on, right? If as the robot rotates around, it rotates in place. And so the diameter of that turning circle it would be the wheel track. And if you multiply that by pi, that's pi times the diameter, right? That's a circumference. That's how far you go all the way around that circle. And if you divide that by 360, because all the way around the circle is 360 degrees, if you divide it by 360, then that's inches, right? Because the circumference is in inches, and that's degrees. So you get inches per degree, right? Because it goes all the way around once, which is one circumference of inches in 360 degrees. So that gets us inches per degree, and then we multiply it by the angle we want, and that's degrees. So what you're left with is inches, and it says how many inches that the wheel needs to turn.
Thank you for that. Very cool.
Is that good?
Okay, that was excellent. Please let
That
us
was
know
our
in
only
the-
question from the chat was about that inches per degree. You guys are just so good. I don't even have to ask it. The question from chat was using wheel diameter versus the distance between wheels. So thank you so much for the detailed explanation.
Sure thing. Okay, so now I talked about earlier what this direction is. Basically, we want it to be at 10% speed, but we need the robot to be turning in the proper direction. So the way to do this is to leverage this cool function called signum. So what signum does is if you have a positive number, it returns 1. If you have a negative number, it returns -1. And if you have 0, it returns 0. So what we're going to do is we're going to do the signum of angle. So if we told it to turn counterclockwise, it's going to go at 10% speed. If we told it to turn clockwise, it's going to go at -10% speed. And if for some reason you told it to go at 0 angle, it's just going to be 0. Okay, so now we go to initialize. Just like in our forward class, we want to reset our encoders. In our execute method, we want to drive again, but this time we want it to drive at 0 speed because we just are turning in place, and we want it to turn in, I don't know what just happened, but we want it to turn in the direction that we just specified in our constructor. Finally, in our end method, we want the chassis to stop turning. So we're going to just call that stop method we used earlier. And then finally for real this time, we are going to check to make sure that we have turned the proper amount. So we're going to see if our distance that the left side of the robot has turned, in fact, is greater than or equal to the inches we need to turn. And that's that whole command. So we're going to go back over to our robot container, and we're going to make another button, and this button is going to be called turn 90. Well, I'm going to call it just turn, but it will turn 90 degrees, and it will use a new turn command that turns 90 degrees. Is the robot possibly working?
Maybe. You have
Okay.
to just make sure it's connected to Wi-Fi.
Okay, so we are going to check to make sure we are connected to our robot. We are. We are going to click simulate. It's going to build our progress. I mean, it's going to
Build our project.
Build our project. It said progress on the screen, so I got confused. And then we're going to select all these 3. I should really set the defaults, but I'll do that next time. And we're going to run it. some stuff's going to happen, and then here we are. We're back at our robot simulation. We're going to set teleoperated enable. We're going to come over here, and we're going to try running our forward command, and maybe this time it'll work. Oh.
It's not working?
It's not working. What the heck?
God, it was working. I don't want to turn it off. It is turned on. This stuff
Okay.
it is enabled.
It is enabled.
Let's see. Let's try doing the other program, the other version of the program which we already had, and then run that.
Oh,
So
okay.
kill this.
So we're going to...
No, go back.
I'll just
Go
kill
back.
it. I'm
No,
killing-
no, go back. Kill this.
Okay.
Okay, and then just go back and run the other version of it, which is sitting there.
Oh, it's...
It's like if you do window or something, it's probably
Yeah.
there.
I don't know where it is.
There.
We could...
No, you hit it. Go to window.
Oh, it's here? Oh, it is here. Which one is it?
The one that's not yours.
Aha! Okay. So
Run that. Let's run this one and just see what's going on, because this one was working. This was working just fine before we just a minute before we started.
This is lovely. This always happens at demos. You'll have to excuse us.
So put it in teleop, go to the dashboard, and hit one of those buttons, like the forward button.
Forward.
There it goes.
Oh my goodness.
There's something we forgot. Okay.
Yeah, there's definitely.
So maybe one of
Okay.
these guys in the
Yeah.
here, we'll
maybe
put it
in
here.
the chat. It could be we didn't initialize our robot container.
There's something we didn't do.
I want to check.
All right, well,
this.
here,
There are
do
a few
forward again.
suggestions from the chat if you'd like to hear the suggestions on
Sure.
what was
What is our
different.
suggestion?
So the first one is that Romi is nervous, which is potential,
That
but
is likely.
not code related.
I am nervous.
The other
that's
is that
more
Grant,
likely is-
you didn't
yeah.
include your sound effects this time, which is if you were showing it what to do with the sound effects, and now we don't have them. But in all seriousness, we do have a question about if the second copy may have still been running. So sound effects aside, maybe as we go through this, there's something you guys can tell our chat about is what the process is when something like this isn't working, right? It can be frustrating. It can be, annoying to work that hard on something and not have it work. But what does the process look like as you break this down and try to figure out what's wrong?
Yeah, I think there's something that we missed. I think when we were writing the program, and so we'll go back and look at that in a minute. And I don't want to put Grant totally on the spot here while we're doing this. So why don't we? Let's see. How are we doing on time? It's almost 2:45. Why don't we do this? Let's we'll go back and look at this in a minute and see if we can figure out what's happening. But before that, let's just look at. So we've got it. So we have it so it turns. Where's the dashboard? That was over here?
Yeah.
Yeah, so here's the smart dashboard. So we have it doing the forward command, which is showing up on the dashboard here. Wait, is
It's
that
not
it?
running. I turned it off. So you can enable it again.
What? Where?
We have to simulate again.
Oh. Yeah, I'm not sure exactly what we missed. But here we go. So here's this, for the other program, here's the forward command. So this,
We're going to aim it the right direction.
is this the right one?
Yes.
I can't see.
Oh,
Wait,
are we
wait.
enabled? We're not
Oh, I'm
enabled.
not. Oh,
We're
not in
enabled.
Telia. Oh,
Okay.
right now we got to be in Telia. We have to be. We're disabled.
Oh, gosh.
All right, we'll get this yet. So here's the forward. It's all this pressure being on
We're
TV.
professionals.
So here we'll start it up. It will go forward. This goes 13 inches in this particular version of the program. We have the other thing which turns. There's two commands. One that turns 90 degrees in one direction, and then it turns 90 degrees in the other direction. And I think that's running the same code that Grant just typed in because we actually wrote it down and, and we've been typing it in. But there's something we missed here somewhere with all the pressure. And then what we'll do next is look at this labyrinth command. And maybe what we'll do is, since it's getting late, why don't we just look at the labyrinth command, and then and we'll show you the thing working, which is the command that does everything. So let me just go back for a second to the slides, which are here, and talk about command groups. Okay, and then we'll figure this out while someone else is talking, and then we'll show you what we did wrong. Another fundamental concept using this command-based programming is that not only can you write subsystems and not only can you write commands like you just saw, but you can also write command groups. And the idea is that, say you want to do a sequence of things, like you want to drive, then turn, then drive, then turn, and stuff like that, which is what you need in order to be able to do this, drive in this little parking labyrinth challenge thing. And so what you can do is you can combine a bunch of commands into a command group, and then they get executed one after another. And there's a whole bunch of different kinds of command groups. The one that we're going to use today is called the sequential command group, and it just runs a bunch of commands in sequence. But there's a bunch of other varieties that we're not going to use today. One of them is a parallel command group, so you can have commands running at the same time as other commands. So if you want to optimize your robot to make it be more efficient, you can have the arm moving while it's driving. You can start both of those going at the same time. There's other versions of the parallel group where these things all kind of determine when it's finished. You know, whether it's finished when both sets of commands are finished, or the first one is finished, or something like that. And that's what these other ones are. So the way you create a command group, we'll just look at one in a minute, so we don't have to do that. We'll look at a command group that's in this project, and so you can see, and that's the one that does this. So here's this version of the project.
That's the one we were just making.
Oh, this is the one we were making? Oh, let's go find the other one. Wait. Window, this one. All right, so here's this version of the project, the one that we just saw that was working. And so if we look at all the files, here's this labyrinth command group. And so what you do for this is you create a command group. You see here it says labyrinth extends sequential command group. So that makes it a command group. And then in here where it says labyrinth, you just add a bunch of commands. And you've already seen forward and you've already seen turn. So you know that forward and turn both work, because you can test those individually. We just did. And we saw them running when you press buttons on the dashboard. So it makes it really easy to kind of build up the program and test it, and then do make it be more and more complex. So what we do here is we say, well, let's go forward for 13 inches because we want to start here, and we're going to drive forward for 13 inches. And then we'll wait for a half a second. And then we're going to turn for 90 degrees, and then we're going to wait for half a second. And then we're going to go forward again for 13. So we're going to go forward for 13. Then we're going to wait, and then we're going to turn. Then we're going to go forward again for some distance, 13. And then we're going to wait, and then we're going to turn. And then we're going to go forward a little bit less, 12 inches, and then turn. And then...
It's helping. It's
Thank
helping.
you. And then we're going to go forward, and we'll be done. We'll go forward 9 inches. So that's how you can combine these to make much more complicated commands, and that's actually pretty interesting. I mean, because your autonomous programs usually do lots and lots of stuff, and this way you can combine these commands together to make much more complicated examples. So if we go back over here to the dashboard and we do this labyrinth command and start it. Are we connected still?
I do have a question from our chat about that command framework, if you wouldn't mind answering. So perfect screen for you guys to be on. I see you with that dashboard up with the different buttons that you can click to create those commands for the robot. Mr. R squared, I can't read, I promise, in the chat. When you use a command framework like that, how do you handle driving with something like a joystick, right? So we're looking at the dashboard with the buttons, right? Forward, turn, etc. But when you're working with a joystick, is there a command that sends the stick movement to the chassis, or how does that work?
Yeah, absolutely. You can create a joystick, and then you can create joystick buttons, and then you can attach the joystick buttons to commands. So when you press the button, the command will run.
Yeah, this is just like normal FRC programming. So we have whole classes dedicated to joysticks. We actually planned on doing this like a couple minutes from now. We are going to make what's called a default drive command, where the default command for our chassis was going to be this default drive command. And it would read the values from this joystick, and then it would set those values as the values for the motors.
But, to be honest, I thought we were going to finish early, but I think we're going long.
I think
but
so too.
But let's see how this works. So here's the labyrinth thing. I just restarted the program. So there it goes. So it's doing the first forward command, and then it waits. Then it does the turn command, and it waits. And now it does the next forward command, and it waits. And then it drives forward again.
Your laptop. Oh no!
And then it turns. And then, okay.
Let's go.
So
let's get a W in the chat, boys.
So let's give a big hand to the robot for being able to pull that off. All right. Just settle down. Settle down.
I was excited, man. That was awesome.
All right. He just got out of high school. You know, he's like a little. He's over. He's been in his house all the time, and
it's been a long quarantine.
So that's kind of the idea, and you can combine these things to make more and more complicated things, and so that's really the way you want to build up programs, because the whole idea is you got all these commands sitting on a dashboard that you just, with one line of code, you get the button to show up on the dashboard. You press the button, it does the command. You start out and you try all the simpler commands, and then you work up to do the more and more complicated commands in the command groups, and eventually you have the entire autonomous program. And that's sort of the idea. So what we want to do now is, let's go back to the slides here for a second, because I think we're done with the Romi for now. Okay, so adding commands to a project, we did that. There's a bunch of shorthand things for creating command groups and creating commands, which you can read about in the documentation. So we're not going to talk about that now, because like I said, we're going a little bit long. But somebody asked about buttons on the joysticks. So you can say when pressed, run a command. While pressed, run a command. When held, run a command. You can say when released, run a command. You can say toggle when released, so that every time it released the button, it toggles, it flips something from to between one state and another state. And you can cancel something when you press a button. So there's all these options, a lot of flexibility using this command framework. So here's how you do a joystick button. You can create a joystick button. Well, you can create a joystick up at the top, like this example stick, where you say new joystick, and then we initialize it with an Xbox controller, and then you can create a joystick button on that example stick variable, and then you can say run the when example button is pressed, run some new example command in this case, or when the button is pressed, you can do the foo command and the bar command when it's pressed and when it's released. So you can you have all these options, all that flexibility. So very, very flexible way of writing robot programs. And as you can see, it just makes it really, really easy to organize your code. All right, I'm going to skip some of this stuff. And what we want, we already did this.
Yes.
Okay, so one of the things that's really interesting is that, and we've spent a lot of time, actually over the last couple of years, getting to the point where this stuff works, is that a lot of times, you don't have your real robot yet. You want to start playing with the program to see how well it's working. You'd like to be able to test the logic to make sure that the program is doing what you think it's doing. And to make that easy, we've implemented some simulation stuff into the library. So you can actually add some code to your robot program and then just be able to run it in simulation mode and then see it working on the screen. And to talk about that, we have Pratik, who's also a member of the WPI Live team, and he did a lot of this stuff. And so he'll talk to you a little bit about how this works and give you an example of how you might create a simulation for your robot. So take it away, Pratik.
Hey everyone, I'm Pratik, and I'm going to talk about a simple, some of the things that you can do with simulations. So I'm going to share a screen here real quick. And then we can go over. So I have a simple drivetrain class right here, and we'll go over some of this code and talk about how we can leverage some of the simulation capabilities. So at the top here, I have some simple constants. So I will start off with the wheel radius. So in this program, I'm going to use meters and SI units for everything, and I'll talk about why a little bit later. So 0.0508 actually corresponds to 2 inches. We can also do something like units.inches to meters too. And then we have our encoder resolution, which Grant talked about. And I believe on the Romi it was 1440, but on your real robot it might be something different. So here I have 4096 as an example. And then we have our 4 motors. So this is really similar to what you would do on a real robot, for example. So we have our left leader, the left follower, the right leader, and the right follower. And then we're creating our speed controller group. So this essentially makes the left follower do exactly what the left leader does, and the same with the right. And then we have our encoders. So ideally, we would put this in a constants class like Grant did a little bit earlier, but just for the sake of demonstration, I have the values hard-coded in here. And then we have a simple gyroscope. So up until now, everything is pretty straightforward and pretty similar to what you would do on a real robot. What we have next here is something called odometry. Now, I'll talk about that in a little bit, but essentially what it does is it takes your encoder positions and then converts them into a field position. So we'll talk about how that will work. So now we get to the simulation part. So in the real world, when you declare an encoder object and let's say you call something like get distance or get rate, it'll actually get the value from the physical sensor and return it to you. But in the simulation, there's no physical sensor to get values from. So what we can do is actually create these encoder sim objects, and then we can feed in our simulated positions and velocities, and we'll talk about where to actually get those values from. And then we have something similar for the gyroscope. So we're going to feed in simulated heading values. What we want to do next is actually create a model of your drivetrain. So what this essentially does is it tries to imitate your physical hardware as closely as possible. So for example, on your real robot, if you give both sides of the robot 6 volts, let's say, it's going to try to mimic how your robot will accelerate for that given voltage, and so on. So to construct this, it's called a differential drive sim. Then we provide a bunch of physical parameters. So let's go through these one by one. So the first parameter over here is the type of motor and how many are on each side. So on our robot, for example, we have 2 Neo motors on each side, but you can also do something like get sim if you're using sim motors, or you can do mini sims or something like that. So you can do get Neo and then the number of motors that you have. What we're going to do next is something called a gear reduction. So for example, on our robot, 7.29 rotations of the Neo shaft makes the wheel shaft spin once. So that's the gear reduction. The third parameter is probably the most difficult to obtain. It's called moment of inertia. What this essentially is how difficult it is to rotate your robot. This is a little bit hard to measure, but a lot of CAD software, if your team uses CAD, can tell you what the moment of inertia of your robot is. But it's not a big deal if you don't have it really accurate. So usually some value between 4 and 9 tends to do. What you want next is the mass of the robot. So usually my team builds robots pretty close to the max limit. So 60 kilograms is about 130 pounds. So that's what we're going to go with. What's next is our wheel radius. So as I declared a constant above, we have our wheel radius right there. So I'm going to put that right in here. And then the track width, which is what Grant called wheel track, which is basically the distance between the left and the right wheel. So in our case, it's 0.712. What the last parameter is something called measurement noise. So for example, your encoders aren't going to be perfect. When you're going at, let's say, 3 meters per second, your encoder values might fluctuate a little bit. And this might mess with some of your feedback control. So what this is essentially trying to do is simulate some of that encoder noise. So what you can do is basically you can measure that encoder noise and put it in here, and this simulator will actually act as if your encoder is giving you that noise. Now, if you can't measure it for some reason, or you're just starting off without a robot, you can actually set that to null, and that will basically make it so that there is no noise at all. And then finally, we have something called a field 2D. So this essentially makes your robot's position show up in the simulator and other dashboards, and I'll show you how exactly that works. Now we'll just quickly go over the rest of the methods in this class. So again, we're going to do a set distance per pulse, as Grant talked about earlier, and it's pretty much the same calculation. So we're going to get the wheel diameter by multiplying 2 times the wheel radius by pi, and then dividing by the resolution. We're just also going to reset the encoders, and then we're going to send the field to Smart Dashboard. So what that essentially does is it sends the field over network tables so that we can see it in the simulator. And then I have a couple more methods. So we have a drive percent, which basically takes a left and right percent. We have an update odometry, which all that does is it gets the gyro angle, it gets the left encoder's distance, and the right encoder's distance, and it basically updates the robot's position on the field. So we'll see how that works when we launch the simulator. We also have another method to reset all of this. So we're resetting our encoders, our simulator position, and our odometry. And all of the documentation for this is also on our docs website. Next, we have a method to basically return the distance traveled by the encoder. So we're just going to get the left distance, the right distance, and then divide that by 2. Then we're going to return our position on the field. So that's what we're going to use to actually show the robot's position in the simulator. So now we come to the 2 most important methods in this class. So the first one is called simulation periodic. This essentially runs only in simulation. So what we're going to do here is we're going to tell our simulated drivetrain, here are the voltages that we're getting from the left side of the drivetrain and the right side of the drivetrain. And then we're going to say, use those voltages and assume you travel with those voltages for 20 milliseconds. So basically, for example, if your right motor says 7 volts and your left motor says 5 volts, the drivetrain simulator is going to use a bunch of physics from these values that you've given it earlier. And then it predicts, okay, so given those voltages, this is going to be your left encoder distance. This is going to be your right encoder distance. This is how fast you'll be traveling. And that's where the sim encoder objects come in. So you can get the left position from the simulator, from the drive sim, and then set that into your encoder. So that's how whenever you call, for example, get distance, that's the distance value that it's going to get in the simulator. But on the real robot, because this method is actually not going to run, whenever you call get distance, it's actually going to use the values from the real robot. So there's no code that you actually have to delete or add when you're running in the simulator or in the real robot. And then our periodic method always runs. It runs regardless of whether you're on the real robot or in the simulator. And then here we're going to update our odometry, and we're going to update the field position. So that's going to make the robot's position show up on the field. What I'm going to do now is write a really simple autonomous program that drives 3 meters and stops. So what we can do is we can write a constant for the distance we want to travel. So we'll say double set point equals 3. And I want to actually send these values to network tables, and I'll show you why in just a second. So what we can do is say smart dashboard dot put number, and then I'll say set point, spell that correctly, and then set point. What I also want to send is what our current position is, and that will help us debug some of the issues that we might have with the PID controller. So we can say smart dashboard dot put number, and then our current position, and then we can call our get drive dot get distance. Now we want to use a simple PID controller to actually drive that 3 meters, so we can declare that over here. So we can say PID controller. And then we can just start off with some basic values. So we'll just take a guess and put in 10 We usually don't want to use an integral term unless absolutely necessary, so I'm just going to set that to 0, and I'll also set the KD value to 0. So when tuning, it's often helpful to send the P and D values over network tables again. So that's what I'm going to do here. So I'll say smart dashboard.put number, and then we'll say KP, and then we'll put in our value of 10, and then put number, and then we'll say KD, and then our 0. Now, because we want to write an autonomous program, what we're going to do is we'll periodically update the P and D from network tables. So that way, when we open up a dashboard, for example, we can actually type in the values that we want, and they'll be updated in here. So we can say PID controller.setP, and then we can say smart dashboard.get number, and then our key is the same as what we put in over there. So the default value for this will be 10, and then set D, we can do smart dashboard.get number, KD, and 0. Next, we want to actually calculate the output from the PID controller. So we can say double output equals PID controller.calculate. Our measurement is basically where we are. So that is our drive.get distance. And then our set point is going to be where we actually want to go. So that's set point. And then we can basically say drive.drive%, and then we'll put in output for the left side and output for the right side. So that's a really simple drive 3 meters autonomous command. Now we can actually simulate the robot code and see what happens when we run it. So we'll wait for the simulator to open. And then there we go. So I'm actually going to make this a little bit bigger, easier to see. So the first thing we actually want to do is, because we sent the field over smart dashboard, we can go over to network table, smart dashboard, and then select field. And now you can see a robot has shown up right there. What I'm actually also going to do is select a field image so that it becomes a little bit easier to know what we're actually doing. And then when we click on this network tables widget and click under smart dashboard, you can see that our KD and KP values have actually shown up. So now let's actually enable autonomous and see what happens. Okay, so that's definitely not what we want happening. We don't want a robot spinning in circles. So let's see what went wrong. So we can go back to our drivetrain class and look at how we're creating our motors. So we've created the speed controller group, the left and the right side. So if you think of positive voltages as spinning the motors clockwise, if the motors on both sides of your drivetrain spin clockwise, your robot's just going to spin in a circle. So we have to invert one side. And you might remember Grant doing this on the right side of his drivetrain. So we can do the same thing here. So we can say mRight group dot set inverted true. And then now we can simulate and then see if that fixed it. So the benefit of the simulator in this case is you can debug some of these small issues with inverting your motors or inverting your encoders before you actually have access to the real robot itself. So now what we can do is enable autonomous. And you can see a robot actually moves forward, but there's a lot of oscillation and we don't want that to happen. To actually visualize this in a better way, we can create a plot in the simulator GUI. So we can say new plot window. I'm going to drag this over here. We can add plot. And what we want to add is our set point, which will show up as a blue line over there. And we also want to add our current position, which is that red line over there. So we're currently at 0, and then the blue line is where we want to be. So if we enable autonomous again, you can see how, so I can pause this plot right here and zoom in. You can see how it oscillates around the set point. That typically means that your p-value is a little bit high. So what we can do here, we can just edit the value right here because we sent the values over smart dashboard. So we can say 5. And then we can enable autonomous again. So let me just resume the plot, enable autonomous. And you can see it's getting a little bit better, but there's still a lot of oscillation. So let's reduce it a little bit more, so 2.5. And then we can enable autonomous again. So that's gotten a lot better. We can also add a D term, which basically dampens some of that oscillation. So what I'm going to do is add 10% of the P, which is usually a good starting point. So we can make that 0.25 and then run it again. And you can see it's a lot better. It still overshoots just a little bit, as you can see in the plot. So we can increase that D just a little bit. So I'm going to increase it to 0.3 and then run the autonomous again. And you can see I'm probably pretty happy with that. And you can, once again, on the field view, let me make this a little bigger. You can see how it nicely comes to a stop at the end. So because our drivetrain actually resembles how the physical hardware will behave, you can actually tune a lot of things like the PID constants that we've tuned over here just using the simulator. So you can actually get a lot of these baseline values before you even have access to the real robot. And what you can also do is in TeleUp, I have a joystick that's connected. Actually, I got to drag the joystick right there. And in TeleUp, you can actually drive around. So I'm actually driving around with a joystick, and you can see the field. The robot actually moves on the field. So that's another cool thing that you can do with the simulator. So yeah, those are basically some of the features that we have in the simulator. There's a lot more, and we have a lot of examples available. So make sure to check out the documentation for that. But yeah, that's a quick rundown of what you can do in the simulator. Back to Brad.
Hey, Pratik, that was like awesome. That was like a really, really good demo. And one of the key things about this that you guys, you know, if you're watching, this is like a really good way of debugging your robot and making sure that everything is working the way that you think it should be working. And you saw how there were some issues in the program, and Pratik was very easily able to identify what the issues were and fix them just while sitting at a desk and not having to get the robot out and drive it around and start it and stop it and, you know, and fight over whether the mechanical team gets the robot or the programmers get the robot or any of the other stuff that happens. So this is great. And so thanks very much for that demo. Okay. Oh, wait. Okay. So what we want to do now is talk a little bit about using this larger FRC robot. But because this is going a little bit long, we're going to kind of show you some of the code that's involved in doing some of this stuff, and we'll talk a little bit about the vision, FRC vision stuff, and kind of, you know, take it from there. So the challenge we want to do that we want to show you today is this. We want to be able to pick up this game piece. Okay, this is you know, we spared no expense in making this field for the robot. So we're going to pick up this game piece with the robot. And then we're going to navigate to this goal, which has this red feather thing that Grant was talking about before. So we're going to navigate to the goal, and then we're going to drop the game piece with the robot onto the field element with the feather on it. And the idea is to use computer vision to be able to find it. And so that's sort of where we're going with this. And so we'll show that. So again, here's the robot that we're going to use. And I think rather than talk about this stuff, let's see, how are we doing? Rather than talk about this stuff right now, I think what we'll do is give you a demo of show you what the thing looks like when it's running, and then Grant can well, maybe we can, yeah, then Grant can well, okay, let's actually talk about this really fast because Pratik did talked about some of this stuff. One of the ways that you can use to control the robot, its performance for the motors, is using PID control, right? And so you saw, Pratik modifying those values and getting and looking at the graphs, and you got to see different responses for the robot. So this lets you kind of accurately position mechanisms on the robot or the robot itself on a field. the way this works is you develop an error, right, which is how far the robot or the mechanism is from where you want it to be, from its set point, and then you come up with these terms: the proportional term, the integral term, and the differential term. Which is the proportional term is just the error, and the integral term is the sum of the errors, and the differential term is how fast the things are changing. You combine these, and then you can get that nice graph that you saw of the thing hitting the set point and not overshooting and doing it pretty quickly. So to make this easy to do in a robot program, we have a special kind of subsystem called a PID subsystem, which lets you embed a PID controller into a subsystem because this is such a common thing to do. And so it's built in, and we'll use that with GearsBot to move the arm and get the arm to the right position so that it can, so it can pick up the game piece and then move the arm to the right position and then drive forward and then drop it onto the box. So we're going to talk about, so rather than create these, we'll kind of walk through what these look like. And we'll do this on, wait, let me just see what's next. Okay. Yeah, we'll do this on Grant's computer here. So I'm just going to unplug the monitor interface. And then we'll move it over to Grant's computer. We'll move it over to Grant's computer. And then he'll show you the code that makes the arm work, the commands that make the arm work, and the commands and the subsystems for the arm. And then we'll show you the thing working.
All right, we are ready to show this code. All right, guys, so this is our ARM subsystem. It models the actual arm on our robot that we will see in just a second. It's by my feet. So it extends this PID subsystem that Brad just brought up. So this PID subsystem, it has a motor, it has a potentiometer, which is a type of sensor. And what it does is when we create a new PID subsystem, we have to give it a P, an I, and a D value. It has these constants that I defined earlier, but it's in the same constants file, the same kind of file that we were using in our Romi example. So these P and I and D values are all just numbers that we set in a different file. We do some messing around with our PID controller. Basically, what this does is it says if the angle of our arm is within 5 degrees of what we tell it to do, we say it's good enough. That's what this set tolerance means. We construct our motor. We construct our potentiometer. I mentioned it's a type of sensor. It's a sensor that tells us what angle our arm is going to be at. That's all that is. And we tell it to, at default, set the arm to be at negative 25 degrees. What that means is if this is 0 degrees, then we tell it to start at this down 25 degrees. So basically, we tell the angle to start. We tell the robot to have the arm start down. In the rest of our subsystem, we have this use output, which is automatically called when this math is done with our PID. Basically, it takes the output and it tells the motor to go at that speed. That's pretty simple. It does some math. It gives us based on the error, how much the motor needs to move, and it tells the motor to move that much. This get measurement, what it does is it gets the value from the potentiometer, and it uses that for the calculations with the PID. And then this at set point, we use over in our ARM system just to see if the arm is at the right place. So that's what this ARM subsystem does.
You want to do the command that?
Sure.
One of the commands that moves it to some position?
So let's look at the arm up command, which we will demo in a sec. So it extends command base. This is just another command. It saves the arm, and it requires the arm. And in our execute method, what we do is we tell the arm to go to 25 degrees up. So instead of 25 degrees down, we do 25 degrees up. And then our isFinish uses that at set point. So this command is over when the arm is 25 degrees up, plus or minus 5 degrees like we said. That's about it for the commands. We also have an arm down command. It moves the arm down to negative 25 degrees. But
are you set up so you can run the commands run off of buttons on the joystick?
Yeah, we can do that right now.
Let's do that. Do you have a joystick?
Well, we don't have the joystick. We have it on the smart dashboard.
Oh, okay.
Which is as good.
Okay.
So if we go to the camera, we can see the actual robot, and we can see it grab our game piece, and we can see it lift it. We don't have manual control of the drivetrain, but we have some automatic control. Do we want to show the final product of that?
Don't do
yet?
the whole thing.
Okay.
Let's just do the arm up.
So we'll just do the
stuff.
arm up, arm down. So, okay. I'm not sure what I'm supposed to be doing right now.
Oh, we'll do. Oh, can we do the robot in the picture-in-picture?
Yeah.
And keep the screen on the big thing. There we go.
Ah, okay.
All right, perfect. And can you, Deone, can you get in there? Okay.
I'll move. Okay.
Perfect.
So here we have our game piece. Here we have our robot. Okay, we put game piece in front of robot. Fix it. Okay. So over on our shuffleboard, which is the same as smart dashboard, just a different dashboard. I like this one more. Brad likes smart dashboard more. I'm going to run the close claw command. So we click it. Oh, we're not enabled. My bad. We're going to enable, and it closes the claw. Amazing. And then we're going to open the claw, and it lets it go. Amazing. Okay, and now we're going to do what we just demonstrated with our code. We're going to bring the arm up. So we're going to click on the arm up command, and it lifts the arm up. And what we can see here, if I come down here, it's maintaining this 25-degree angle. So what we can actually do is if I try pushing it down, it fights back and it kind of springs back up. So it's using this error loop where it sees how off the arm is, and it uses that error to determine how much effort needs to go into the motors. So if I walk back over here, if I tell the arm to go down, it zips down and then it stays at that position.
Okay.
Yeah.
So the commands that you just saw were just written to the smart dashboard, and so you got buttons, or in this case to the shuffleboard. So you got buttons that correspond to those, and then when you press the buttons, then the command runs. So again, it's kind of showing you how easy it is if you break up your program operations into commands to be able to test them individually. So that's like a really cool feature. All right. So the next thing we want to talk about is actually being able to navigate to that box, to the feather. And yeah, let's do that.
Okay, we're going to switch.
So we're going to switch the computer over to my computer, or switch the video over to my computer. Oh, good. Okay. So yeah, we just turned it off so it won't be too jarring. And let's see here. Okay. So I think we should be. Are we back? Wait a minute.
Oh.
It's thinking about it. All right, we should be back. Okay. So so you saw that. So we want to talk a little bit about computer vision right now, and it's really nice to add because you like to use computer vision on your FRC robots or even on the Romi. You can do this by having a webcam and adding it to the Romi robot. And there's a bunch of ways of doing it. This is for how to do it on the Robo Rio. You can connect USB camera right to the Robo Rio, and then you can run the vision code on the Robo Rio. But these days, computers are these little microprocessors are really, really fast. So that works, but it may bog down the robot program, or it may bog down the vision program. Another way of doing this is you can stream the vision, the stuff that's coming from the camera, back to the laptop, and then process it on the laptop, and then send commands back to the robot over network tables in order to tell it what to do. And that's another way of doing this. But the way that we've kind of preferred lately is to put a coprocessor on the robot. In this case, we're using a Raspberry Pi. That's the one that's most popular. And stick that onto your robot and connect the camera to the Raspberry Pi. And then the Raspberry Pi does the vision processing and then tells the Robo Rio what to do. So there's no delays over the network or anything like that. It's just all local on the robot. And so we're going to talk a little bit about how to do that. Question, Libby?
Yeah, we do. You're always on such a roll, and I never want to interrupt you. So, and I'm having fun learning about this as well. But we have another question from Mr. R Squared in chat. Can you have because you mentioned that you can do some of this work on the Romi robots as well. Can you have vision running concurrent with Romi control software on the same Pi?
You can.
Yes. Yeah, and that's the idea.
Ooh,
So
fancy.
so you can test that stuff. And the nice thing is that because it's everything is using this network table stuff, this communications layer, you can send the results of the vision processing on the Raspberry Pi back to your robot program that's running on your desktop. So you can play with all of this stuff. It's kind of nice. So what we're going to talk about now is this Raspberry Pi image and how versatile it is. And so I want to introduce Peter Johnson. You guys may not know Peter, but you've used his stuff, okay? Because he like cranks out code like a madman. So the new version of network tables is something that Peter did. The software that runs on the Raspberry Pi is something that Peter did. And you'll see some of this new dashboard, the simulation GUI stuff, is stuff that Peter has done. So he's fast. And so we're going to switch to Peter now, and he can talk about how this new version of FRC Vision works, WPI Lab Pi, and how you can program your Raspberry Pi to work with your robots. So take it away,
Sure.
Peter.
Yeah, it's great to be here. I'll talk through the kind of the Pi pieces of it, and I'll do that by sharing my desktop. So I'll switch over to that, and we can start walking through what all is here. So let me do that real fast, and then quickly switch window. Doesn't confuse everyone. So hopefully that's coming up here. My desktop. Essentially, what I'll talk through is what WPI Lab Pi is. So last year or the year before, we created this kind of standardized Raspberry Pi image called Vision, and the idea is it's an SD card image. So you download the image off of GitHub and use a etcher by Belina to actually write that image to an SD card, and then you put the SD card in your Pi. You can just turn on the Pi and it comes up, and it has everything you need to deal with. So basically, it has all of the pieces. It has a vision stream application built in, and of course, this year we added the Romi image to that. So now there's actually two variants of this. One, the same thing for FRC Vision before. So it's got image processing. So you can do grams on it, and then we added on top of Romi piece. When you image Romi, it would download the Romi version of this image. It has both simultaneously. I saw that earlier. So essentially, this image will work. We've tested it with Raspberry Pi 4 and 3B. It should work with back with Raspberry Pi 2 as well. It should work clearly for vision processing. You want more and more than what the two can offer, but certainly for the Romi, that should be between these other than the fact that
Peter?
the Romi image. Sure.
Peter, we're running into, I'm sure we'll have some questions in chat in a moment, but we're having just a little bit of trouble understanding your audio. Could you refresh the page you used to connect to our call just for a moment to make sure that we're getting your audio fully and people can understand you all the way? We want to make sure that everybody can hear it and take part. So if you wouldn't mind refreshing and coming back in, because we want to hear it.
All right, am I back?
I think so. I can hear you.
Okay. All right. And I'll share again here.
Awesome. Thank you so much. And thank you, chat, for being patient with us. Of course, we want to make sure everyone can hear it. Thanks.
Yeah, sorry about that. The main difference between these two images is in the networking aspect. So the from the Raspberry Pi perspective, the Pi does, of course, have support for Wi-Fi and Bluetooth, but when you're using a vision coder on your FRC, full-size FRC robot, not legal. You can't do a legally field because the field uses Wi-Fi to connect to the robot. So the standard image disables Wi-Fi. So it's all kind of comes off the shelf with all that disabled, and you have to use that port. with the Romi version of it, it actually comes pre-configured with as an access point, so it'll actually create a Wi-Fi network called WPI libpi, obviously, and that's what we're going to use to connect to the Pi when you the image. So one thing is when you go to GitHub to download this, there's a big About page. If you scroll down to the Assets folder of it, you're going to see two versions of the image. So if you're using this with the Romi, you're going to want to use the one that says -Romi at the end. Then you download that to your desktop. There's some instructions here as well as on the WPI lib documentation on how to download Etcher and image card, but I've already done that here at home, so I've got a Romi that's up and running, so I can go down to my network here and I let Pi. Now we did set it up with, we didn't want just to have it wide open, so there is a password set up on it initially, which is on this page. It's super secret, secure password of WPI lib 2021 exclamation point. A little bit more secure than 12345, but we'll go ahead and connect to it. So again, the first time you power this up, it'll take a little bit longer to configure, but once it's gone first boot process, times you boot it later, it only takes about 20 to 30 seconds to start up. So this will take a look here. It has to think, Windows has to think through actually connecting to. But coming up very shortly here. Essentially, what I'm doing the demo today with, again, is with the Romi. The main image without the Romi bits works very similarly. So when you first bring it up, you want to connect to 10.0. The other way you can connect to it is with wpi.local. With the Romi image, it's really easy to connect just to that address. And up comes the dashboard here. So what this page lets you do is it gives you both status of me as well as about the vision I'm running, and lets you make changes as well. So there's some tabs along the left-hand side. There is what's new this year, of course, with the Romi and the Romi version of the image is the Romi tab. So if you click on that, it gives you to both do some configuration changes as well as checks on status. So for example, that shows you the battery voltage here, whether or not the firmware is compatible, what the version of it is, etc. It provides ways to update. You can update the web service. You can change the I/O configuration of the Romi. So this is something that, again, folks like ZQ added. Allow configuration of these 5 different I/O ports on the Romi. You can set each one to a digital, an analog, or a PWM. You can also update the Romi firmware. So this does require a little side. You have to plug in a USB data cable between the Romi and the Pi in order. But this also allows you to update the firmware. And clearly, when you first get the Romi out of the box, it's not going to have the right firmware on it. So this is one of the setup steps that you'll need to do when first setting up the Romi. There's also some output here, which has Able over on the right-hand side to let you see the output of the Romi service program for debugging. You may notice the up along the screen, there's two buttons here, read only and roll. So one of the things that this Pi image does is it sets the Raspberry Pi file system. So all of the disk storage on the Pi is all read only by default. So you can hard power off the Pi. You don't you think about on Windows if you just cut the power rather than safely shutting down, it has to do a bunch of stuff when you start it back up. What we did with the Pi image is we set it to everything read only. So because really things don't need access when we're running to write to the image. But that way, if you off the Romi, it's okay. It doesn't corrupt the file system or get anything wrong there. But when you want to make configuration changes, you have to go over here and click the writable button to make the image writable. So I'll talk a little bit about the Romi piece. I'll also talk about the vision piece of it. So on the vision, there's under vision settings, there's some options to create cameras. So in this case, I have just a standard USB camera hooked up off the shelf. And the image comes pre-configured with a setup for handling a single USB camera, but you can add more cameras as well. So there's so it's all done through this dialog. So we can say writable here, and you can say add connected camera, and that gives you what other cameras are connected. So right now, these options, BCM 2835, are the built-in Pi camera with the ribbon cable style. But I do have this USB camera already connected. It's a camera name. It lets you change some settings. So you can set the pixel format that it's the camera width, what the width and height of the video stream is, etc., and set the balance to white balance. So what I'm actually going to do is I'm going to I'm not going to change any settings here. This is pretty much how it comes pre-configured. But what I will do is there's also this green button up here to open the camera stream. So what that actually does is it'll open another tab in the browser and camera stream. So here we have the video camera. It's just showing a picture of my laptop camera. I can certainly hold over and there's something like that, and you can see it's a live view that we're seeing there. And this page also gives you a bunch of things dynamically configured. So you can change the settings, change the contrast, saturation, etc. It also gives you all the video modes down at the bottom. So if you have a USB camera that supports like resolution video mode, you can go and change that in the camera settings as well. So as an example, I can change it to 640 by 480, get a little bit higher resolution view, change the width and height here. And again, I clicked on writable to make this writable and save, and it means and then restart the camera. It takes a few seconds to do, but then we can, I'll close that tab and reopen it. So now you have much higher resolution camera stream that we're getting. So this is kind of the camera stream. In addition to that, this also ability to upload a vision application. So again, this is completely separate from the Romi part of it. So you can do this on the Romi as well. There's a built-in multi-camera streaming application, which is what's currently running now. But you can download example programs for Java, C++, as well as Python to create OpenCV-based programs, and then you can re-upload them through this interface. The status tab is then to display the output from your Vision program. And the last tab I want to hit on, just configuration standpoint. So there's a fair number of network settings you can set on this. What I would recommend if you're using the Romi is just changing the SSID. You can leave everything else the same. But particularly if you might have multiple Romis operating in the same environment where you have, say you can meet in a group as a team, with 2 or 3 people, something like, and you want to run Romis in kind of a competition environment, you can use to set the SSID and optionally change the passphrase. Clearly, if you do this and change the settings sufficiently, we're accessing the web page through the web itself. So it's pretty easy to just lose connection through this. So definitely be careful when making changes here, but it's pretty low risk to change the SSID. Just tack on a team number or your name. And again, you can click writable and hit save to change there. If you change the SSID, you're going to have to, of course, it'll disconnect you from it if you're connected through Wi-Fi. So go back to your network to reconnect to the new network. But these are some of the options that are here. Again, with the 2 variants of the Raspberry Pi, when you're running as a cursor, it's not going to give you the Wi-Fi options, but you can set the different Ethernet options on the same page as well. So one recovery might screw up something on the Wi-Fi side is plug in an Ethernet cable and also connect to the Pi through Ethernet, or you can just re-image the entire SD card if you re-image the SD card, put the SD card back to factory, quote unquote factory settings. So that's much all I wanted to go through. We Raspberry Pi. I'm not going to demo creating a video, hand that back to Brad to do. This is kind of the Raspberry Pi and settings, and again, you can use it both as a coprocessor as well as on your Romi robot itself. So back.
All right.
Okay, we're back. Thanks, Peter. That was great. All right, so what we want to do now is, so we used that Raspberry Pi image, and we did some computer vision stuff on the little robot that we have here to be able to navigate to that box with the red target on it. And so we want to show you how that stuff works, show that running. And we want to show you just how we created the vision program, which is another really cool program that's in part of the WPI Lab suite called Grip. Do you have that?
I have Grip.
So what we'll do is Grant will show you how he used Grip to create that. Oh, I got to give you the laptop. So I'm going to switch the laptop over to Grant's computer, and we'll show you how we created this Python program that could do the vision stuff, that could recognize the feather and be able to go to it using OpenCV. So Grant, go ahead and...
Okay. So here we are in a tool named Grip, and this was made by some WPI students several years ago. And it's really, really nice for developing what's called a vision pipeline. And what that does is we're able to take an image and get useful data out of it. So what I'm doing right now is I'm telling my Grip to use the camera on the robot as the default camera. And now it's letting me hit OK. OK, whatever. So now, if I drag this in, we can see what the heck is going on. So over on the far left, we have what the robot is able to see. I'm going to remove some of this stuff. Okay. All right, so on this far left, we have this image. And this is what the robot is currently able to see. If I put my fingers in front of it, we'll see it in a second. Whoa. Hello. Why can't it see my fingers? Oh, it's just being a little slow. You have to excuse it. But anyway, so we have this image in front of us, and what we're going to do is we're going to go through a series of stages, and we're going to filter out colors, and we're going to detect lines, and basically what we're trying to do is we're trying to find this red feather. So the first step is this image has a lot of harsh lines and everything, so what I wanted to do is I wanted to blur it a little bit. So if I click this eye down here, what I've done is you can see clearly on the right that it's not so clear. It's a little bit blurred, and it makes the lines a little softer, makes the colors blend together a bit more, makes it easier to do some detection. Next up, we have what's called an HSV threshold. So I'm going to reset it, and then we can all work together and do something really cool. So on the left, we have our blurred image, and on the right, we have the result of our HSV threshold. And what HSV stands for is hue, saturation, and value. So each pixel has a hue and saturation and value. The confusion about the value is like a brightness, so that's what that means. So each pixel has these values. And what this thing on the right is, if it's a white pixel, that means it passes through this filter. It's within these ranges. If it's black, that means it doesn't pass through these ranges. And what our goal here is we're trying to get everything but this red splotch. We're going to call it a feather because I originally got it from this turkey hat that WPI gave out. Yeah, it's a red splotch. So what we're going to do is we're going to start with our value. And we're going to tune the value by dragging the slider. And we're going to try to move it until we get some useful stuff. So you can see how our background's disappearing. And we can kind of see our box now. And wow, that was actually really good. You can see like most of the feather right now. In fact, I think I went maybe a little too far. And now I can't even see the left one. No. Gosh, I can't even see the left slider. I might have to drag it in. I'm gonna grab another HSV threshold. So all you do to drag in a new thing is you go on this right side, it says HSV threshold, and I drag it over. And what I do is I connect the output of the blur to the input of the HSV threshold, and I connect the output of the HSV threshold to our next thing that I'll talk about. And then I show this again, and then we'll try it again. So we'll drag the value way over, but not too far this time because we don't want to break it. We'll stop it this far, and then we'll change our saturation. Oh yeah, this is working really nicely. So we can kind of see our feather. I'm hesitant to adjust it more, but we'll go about this far. We'll go to our hue now. We'll start changing that. Oh, that didn't work at all, so we're going to put it back, and we're going to go on the other end. And we're going to adjust this end. Doesn't really seem to be working so well. So let's go to the upper end of our saturation, because that's not something we've changed yet. And this is starting to look pretty darn good. Okay, so I kind of accept this. This is good enough for me. What I will do is, this is actually our game piece, so I'm just going to take it out of the image. And now we only have the feather, so that's really good. The game piece would never be in the image because it would always either be in the claw or we wouldn't be using vision to detect it. So we're only using vision when we're scoring the game piece, so we're never going to see the game piece.
And if you wanted to isolate it a little bit better, there's possibly other filters that you could apply.
Yes, definitely.
So you have to kind of play with it. And the idea is that on the right you have this whole palette of all the OpenCV operations. You just drag them in to make this pipeline.
Yeah, so this is just like a simple pipeline. There's only 5 things, or 4 things. But anyway, now what we're going to do is we're going to use this find contours operation. And it sounds scary, but all it means is we find the border of this. So if I show you what it does, look at that. It takes our big white splotch and finds the border. Amazing. And then we have this filter contours operation, and you know, it's there. It filters out contours that, like if we had another red object like over here that was a little too small, then we could like filter out the smallest objects. And you know, there's only one object here, so it doesn't really matter. But that's what you would use it for. And then once we're done, we do tools, and we do generate, and we generate code. We get some Python. And I like this Python, so I'm going to click OK. And now we have this Python code generated. And if we go over to our Vision project that we've already set up, and we go over to my main script, we're just going to build it. So this is this custom build script I made. You don't have to go so far as to do this. You could do this all in one file. But we can look at the generated code. So here is grip.py. This is what the grip tool just generated for us. And it comes up with a ton of code. Like this saves me like an hour or 2 of my time. Like this is just hard, like API calls, stuff that's like really difficult. And this grip tool is really just great for doing like stuff like this that you're gonna do again every year. So I really enjoy this tool. So now that we've built our thing that we're gonna upload, we're going to go over to the web dashboard that Peter was showing us, and we're going to go to the application. I'm going to upload our own...
You don't have to do it.
Well, I have to retune the pipeline anyway.
Oh, I see. Okay.
So we're going to upload it. Okay, so now we have the code on there. We're going to restart our code. And in a second, what we're going to see, well, in 5 seconds rather, what we're going to see is it's outputting this thing called contour, and then there's a number, and then there's a number. So what the first number is, it's the center X coordinate. So if we look at our actual image, it's telling us the center X coordinate of that feather, and the second one is the width of the feather. So it was saying like 300 as our center X, and the width of our image is 640 pixels. So 300 is roughly half of 640, so it's saying it's roughly in the middle, which I definitely agree with. This looks like in the middle of my image. And it's saying the width is 30 pixels. The width of the whole image is 640. This, sure, I'd say that's, 40 pixels or 45 pixels. I agree with this. This looks like real data, and it's being very consistent, so I think this is working well. So now we're going to go over to our dashboard, and are we ready to demonstrate this?
Sure, we could run the program now.
Okay. Do we want to show the robot code for the vision?
No, let's not do that now. So we're going to post both of the programs, the Romi program and the GearSpot program, and to be able to see those. So keep an eye on WPILive.org, and we'll put them up there so you can download both of the programs and see what happened. And we will figure out what was wrong with the Romi program and show you the corrected version of it.
Okay, so if we pan over to our camera now, we're going to demonstrate this whole goal that we're looking for. So what we want to do is we want to have our claw come down, and it's going to grab our game piece, and it's going to bring our game piece all the way over here to on top of this box. And here's the vision target right here. So let's see if it works. We're going to enable now. Oh, it missed the grab. Oh no. But look, it's following the vision target. It ran right in, and then it would drop it off. So it uses our vision data properly, and it's able to navigate all the way to our box. I guess I didn't put the initial game piece in the right place, however, so it was not able to grab it. We don't have any fancy logic for, in fact, grabbing our game piece. So if I'll reset it, and then we will try it again. Second time is, in fact, the charm. This is known. This is an expression, right? Second time's the charm. Okay, so we've reset. We put the target back in place. And we'll give it a go in 3, 2, 1. It missed it again. Oh my goodness.
All right. Well,
yeah.
So this actually worked.
Yes.
Before we started the broadcast. But yeah. But I mean, so if you're writing a FRC program, rather than do something that you throw together like in an hour, you can be a little bit better about it, and then you can do this. The other thing that's interesting that Grant didn't mention is that he's getting the width of the feather back as one of those parameters through network tables, and that allows the robot program to know how far away it is from the box, because the further away you are, the smaller the feather looks in the view, and as you get closer, then it gets bigger and bigger, and so you do a little bit of trigonometry, and you can figure out how far away you are. So it's a really good method of approaching a target and then doing something with it. So
you want the?
I'm trying to decide. No, I think we'll leave it on your laptop for now, because we're going to switch in a second to Tyler. So this stuff is really nice. I mean, so you could use all the FRC Vision stuff to navigate to those retroreflective tape targets. You can find stuff on the field. Some people are even doing machine learning, which we will talk about again at another time. But using all these techniques to be able to see stuff. But if you're at the other end of a 50-foot field, and you want to be able to navigate to where the camera can see the stuff, then you need to have some good way of doing kind of precise navigation on the field and being able to, be able to follow a path. And the path may be complicated because you may have to drive around field elements and all kinds of stuff. And so there's a whole bunch of stuff in WPI Live that lets you do that makes it really easy to generate those paths, do this trajectory generation, to do trajectories that the robot can follow, and even kind of motion planning and trajectories for mechanisms on your robot, like arms and elevators and stuff like that. So for that, Tyler Vanessa we're gonna get him who wrote a lot of this stuff, and actually wrote a book that you guys can find online about how all this stuff works. And he'll talk to us a little bit about how the capabilities of the libraries and how you can do that. So is Tyler there? Oh, there
Excellent.
He is. Hey, so Tyler,
Hello.
Take it away here.
All right. So I'm going to give everyone an overview of some of the newer model-based control stuff that we've added for this year. And I'll share my screen real quick so we can get started. All right. So first I'm going to show you kind of what is possible with some of this stuff. And so like with my team's robot, like this is using a lot of the, I'll go into each component that this uses in a bit, but this is kind of what you can do. So as you can see there, we were able to follow a curved trajectory and pick up other balls and then shoot them. And all of that was in autonomous. And when you're designing a like a control system like this, there's a couple different components. So I'll go over some definitions first. So like, and this diagram will be seen throughout what I'm talking about. So there's the first thing is like you need a model for how your robot behaves, because for a lot of the other stuff you need to know how it behaves to tune everything correctly, especially in simulation. You need to know where your robot is on the field, and then once you know where you are, you can plan a trajectory to get from here to there, and then you need control to actually get you there and to follow that motion profile. And WPI Lab has a lot of features this year that will make all of that a lot easier. So like a lot of the stuff on that robot you just saw was all from WPI Lab. We didn't really have to do much custom stuff. So as for what modeling is for, so a model is just a set of equations that tells you, like you give it some inputs and it gives you an output. So an input would be something like a motor voltage. And then the output are the sensors and things that your feedback controllers will use. And that's what that differential drive sim class does, as an example. And that gives you more accurate drivetrain sims. And you can also use that model to auto-tune your control loops. So like you don't have to do trial and error anymore. And like with that robot you saw, we actually just used the stuff in WPI Lab, and the control gains that came out of it were pretty good out of the box. It's like, so as long as you get an accurate model, you'll get a good controller. And some ways you can get a model is by using this thing called the characterization tool. And I'm going to provide links here throughout because just for time. Then you can go to docs.wpilab.org to see more about that. And there's some tutorials and other things. So the characterization tool measures all your encoder data and your gyroscope data for a couple moves, like adding, like setting a voltage and then looking at how it accelerates, and also what the steady state velocity is for different voltages you apply. And it lets you build up this equation that represents how your robot moves. And then you can use those to generate a model using some of the functions in WPI Lab. And then you can use those later. So localization is like the odometry thing you saw earlier, where it takes in measurements and then figures out where the robot is on the field. And you normally want to do this for a couple of reasons. One is that if you're just using encoders and driving in a straight line, like it doesn't always move in a straight line, and you can accumulate errors because for the same encoder movements, there's multiple, like for the same encoder measurements, there's multiple ways to get to the same spot. And so you don't necessarily know, like based on those, where you are. So you need to incorporate multiple sources of information. And that's what localization, that's the process of doing that. And you see here, like we set a set point, and then like that goes into a controller and actually controls our robot. And the odometry takes your measurements, and that informs your controller. Because once you can see it, then you can do something about it and get to, and like compensate for that error to go where you want. And here's some of the classes that we have that do this. There's the differential drive odometry class, which you've already seen. And we have a docs page that goes into that. And then there's a new class we added this year called the pose estimator class, that it's actually a drop-in replacement for odometry, but it also lets you add vision measurements. So like when the encoder and the gyro like accumulate error because your wheels slip, like you see a lot of teams do this where they use their vision to aim their robot at the target to actually shoot a ball. And this pre-packages the corrective math you need. So all you got to do is call add measurement, and then you give it the vision measurement, and then it automatically adjusts your odometry. And which is really helpful because like with that robot you saw in the video, we get about 7 inches of error on that turn because of the pneumatic wheels. And with vision, you can compensate for that, and it works great. So now that we have a model and we know where that model is on the field, now we need to plan how to get to where we want to go, and you can use motion profiles for that. So how is this different from, say, a PID controller? You just set like 10 feet that way and then say, go there. Well, that can have reproducibility problems because the set point is moving faster than the robot can actually move over time. So you start to lose control over what the robot is doing moment to moment. So what a motion profile lets you do is change your position from where you are to where you want to be in a controlled fashion that the robot can actually achieve. And like on the left is a trapezoid profile. You can also have S-curves. And it's like the whole idea is you limit the accelerations so that the robot can achieve them and compensate for any disturbances if you want. Makes things a lot more repeatable. And then these are 2 different classes we have for that. There's a trapezoid profile class that lets you filter. Well, I call it filter. It's because you can put in set points and it will apply constraints to it and say, I want this to go at a max velocity and a max acceleration. And it will automatically just give you a value that obeys that. And we have a profile PID controller class that wraps that up for you. So you can just give it a goal, and then it automatically gives you a set point that follows the profile. And the CTRE Motion Magic basically does this, but this is built into WPI Lab. So it integrates with the ecosystem a bit better. And one of the other benefits of motion profiles is that it makes it a lot easier to tune your controllers, because since you're compensating for less error, the controller has to do less work. Yeah, and here's some example of 2-dimensional motion profiles. So like a drivetrain S-curve. And then this is the S-curve you just saw in the video. We get an XY position for the robot, and then some wheel velocities, and then we tell the controller, do these at each time step. And this is some links to some of the trajectory generator stuff. And this is how we were generating that trajectory. There's a tutorial that walks you through, here's how to set up your robot program with all the sensors and stuff, and then here's how to actually set up your controller, set up the motion profile, and it goes step by step. So the next part, now that we have a model, we know where we are, we know where we want to go, how do we actually get there? So for that, that's what these 2 boxes here are for. So there's a feedback controller and a feed forward controller. Feedback is like PID. Like you take information like your measurement and you feed that back into your controller calculations, and you can compute an error. And that's that part of this block diagram is. And then you can use that to apply corrective actions. So like the voltage can be modified to drive it to where you need to go. One of the other things that having that motion profile gives you is, now that you have a profile the robot can actually follow, you can work backwards to figure out, well, I know how it should behave, so what voltage should I apply to make it behave that way? And we have some classes that facilitate that for you. You can just take the data from FRC characterization, take the gains it gives you, which is like 3 numbers. You throw it into the motor feed forward classes, and then it gives you a voltage out. And then you just add that to your motor output. And so that will cause the robot to roughly follow your trajectory already. And then all your feedback controller has to do is just pick up the slop. because like battery sag and other things like that. And the feedback controller is a lot better at doing those sorts of things. And then you can also do other things like the compensating for gravity, or we can have gearbox friction, where you just apply a small constant offset to get things moving. Yeah, and we have a documentation page on different types of feed forwards and more details on what they are and what they can do. And then for feedback, there's 2 different levels that robot was using. There's the PID controllers for like the wheels, so we can get the robot moving at certain wheel velocities. And then an upper level controller that deals with the robot's position on the field. So we know where the robot is and where it needs to be in X, Y, and the heading. And so that will output wheel velocity commands for that lower level PID controller. And then something else we added for this year was the linear quadratic regulator, which is basically a P controller, but we use math in that model we got earlier to choose the gains for us. So we don't have to go through trial and error of tweaking the gains. Like, we can just get good gains out of the box. And like once we had like 2 days before competition with that robot to actually get things going, and it only took about a day to get everything ironed out, because what we got was just, it worked, right? Because if your model's right, and if the control is good for the model and the model matches reality, it has to work, right? As long as you work out like the encoders go the right way, the motors go the right way, those sorts of things. And so here's a couple more links. So like there's the documentation page, and a lot of this stuff, like, it's very highly abstracted for teams, so that they don't really have to worry about the math to actually use them, because like a lot of this math you don't see until college. So we want to bring like higher level robot control to more people. But if you're curious about how that stuff works, you can go to that link there. That's a link to the book Brad mentioned, and it goes over like all these different categories with your modeling, your localization, your motion profiling, and your control, and breaks down in a lot more detail what the models that we provide, and like how all the math works behind the scenes. So that's so here's some data for like what that simulated robot was doing, and you can see how we got that 2D trajectory there, and then here's the velocities that was getting applied over time, and you can see the voltages here and how closely all of that tracks. And that's because we have that feed forward there to like compensate for things before it becomes a problem. Yeah. So that's all I got. I guess back to Brad.
We good? Oh,
Yeah.
Okay. All right. Hey, thanks, Tyler. That was awesome. And for all you guys who've been watching, I mean, it sounds a little bit complicated, but this is like really a great way as you learn more and more about how this stuff works and more about robotics engineering, you can start using some of these more advanced features to get really, really good, accurate control of your robot and get it to do exactly what you want, the performance that you're looking for. And so that's sort of so we put this at the end, but it's a really, really really significant amount of work that Tyler did to get this stuff all into the library. And
Pratik helped too. We have a whole team of people.
Yeah, we have a whole team.
Yeah, that's true. I mean, there's a lot of people working on this. There's the robot characterization tool that works with this stuff and comes up with the constants and the values you need to get the most optimal efficiency with the robot, and a bunch of other stuff. So I hope you guys enjoyed the day. I guess I want to thank everybody for participating, especially the developers who came in from took off the time on Saturday afternoon to come in from from California, from wherever they were and participate. And I want to again also thank Grant, who's been out here with me, and Yoni, who's in the who's been here working some of the cameras and stuff, and Jacob, our producer, for putting this thing together. And so thanks a lot. And let's go back to Libby and kind of finish up.
Absolutely. Thank you so much for joining us today. I also have one more shout out to give. I want to say thank you to Sonner. I hope you're saying your name right in the chat for the raid. One of the coolest things in the Twitch community is that you can share your channel and your audience with other streamers. So those who stream rating this channel, thank you for sharing communities with us. As a first alum and a first mentor, I just want to say I've mentored for 10 years, but I focused mostly on mechanical and strategy, and learning along with all this code stuff with you guys has been so much fun. We've learned a lot and we've covered a lot about coding robots today, which makes perfect sense for Computer Science Education Weeks. We've got lots of links and resources in the chat, and the materials from our streams will be archived on the Twitch channel and on YouTube, so don't forget to share those with your teammates and your first community friends. Thank you so much to Brad and Grant for the WPI Lab Control System team, as well as to our guest presenters today for sharing their knowledge and their experience as they've taught us this afternoon. Of course, there are always more shows coming up on First TV. The big one we've all been waiting for, of course, being the first robotics competition kickoff on January 9th, 2021. Boy, it feels good to say 2021. Make sure you follow this channel. That's twitch.tv/firstinspires to keep notifications on so you never miss an event. It's always a party over here. Thank you to everyone for tuning in to First TV. It's been so awesome to spend this hour or, a few hours of code with you. We want you to have a great day and a safe rest of your weekend. As we head out, we're going to remind you of that something awesome from the top of the show. This holiday season, Star Wars Force for Change, Disney, Lucasfilm, and LEGO teamed up with First to bring fans an exciting STEM challenge for all of our at-home innovators. Make sure you submit your festive builds for the Star Wars LEGO Holiday Contest. So let's check that out one more time, and we'll see you next time here on First TV.
Hi there, Star Wars fans! Kelly Marie Tran here. In the LEGO Star Wars Holiday Special streaming on Disney+, Rose, Rey, Poe, Finn, Chewie, and all your favorite characters come together to learn the true meaning of Life Day.
Gimme! Galaxy's best Emperor. Meh!
Now, with the holiday season upon us, we want to keep the Life Day magic alive by seeing you become forces for cheer. As part of the Star Wars Force for Change initiative, Disney and Lucasfilm are once again teaming up with the global robotics community First to bring you an exciting challenge. Through First LEGO League, students around the world are introduced to the basics of robotics and engineering, using LEGO bricks to build unique solutions that teach coding, creativity, and teamwork. Together, Star Wars Force for Change and First are challenging you and your family to put your design skills to the test. We want to see you reimagine your LEGO bricks into Star Wars holiday-inspired builds. That icy rebel outpost? A winter wonderland. Those colorful lightsabers? Twinkly festive lights. The Millennium Falcon? Try the fastest present delivery vehicle in the galaxy. Share a photo of your reimagined LEGO Star Wars holiday-inspired builds on Instagram or Twitter using hashtag LEGO Star Wars Holiday Contest. And don't worry, Rebels, this is not a trap.
It's a wrap!
5 winners will be chosen to receive some exciting LEGO prizes. Our grand prize winner will receive a LEGO Star Wars Millennium Falcon and a First LEGO League team or classroom registration.
So cool!
And 4 runners-up will receive a LEGO Star Wars Sith TIE Fighter, Poe Dameron's X-Wing Fighter, an AT-AT, the Razor Crest, and the Child. That's 5 things. Not a bad bounty, right? So come on, builders. You're our only ho-ho-ho. See what I did there? And be sure to check out the LEGO Star Wars Holiday Special, streaming now on Disney+. And may the Force be with you.